morning. Let's start. So we have three lectures today, and the first speaker is Kentaro Omori, and he will tell us more about non-invertible symmetries.
Thanks, Amin. So let's start the day 2 lecture. So I start from commenting about the last lecture. So on some part I think I didn't do a great job in explaining. So I want to comment. So I said that given a symmetry, conventional symmetry so far, that there's a corresponding symmetry of topological operator. This is topological operator given for each element of your symmetry group. And so I gave you a definition for a bounded when this is bounded, but it's more it can be generalized to more general sigma 1. So this is codimension 1 surface, and so that should be defined by this. So okay, so let's assume that your theory is weakly coupled and described by a field phi, and have this operator. Then on this operator, let me just call this field value on this side of the operator to be phi L, and this is phi R. Then here, so first you cut your manifold into patches so that this operator is the boundary of your patch, and here you glue. So instead of path integrate over the field with a smooth configuration, you along this operator you glue the field value from both two sides by twisting by G, and then you do. So you do the path integral over this kind of configuration. So this is nothing but the so-called twisted boundary condition. When you do, for example, torus, and put your operator like this. Okay, so this is not bounded, but you can define this operator by this, and okay, and this is nothing but the twisted boundary condition that if you go around this cycle, your field value gets acted by G. Okay, so that's the definition. So in particular, in this case, if you regard this as a imaginary time, then of course this computes the trace of the twisted partition function this trace. So that's a standard thing. And so yeah, I also failed to mention an important thing, that for U1 case, the topologicalness of this thing. So this thing is just a netto charge, and so that comes from up to corrections. That's and that topologicalness of course comes from the topologicalness of network charge, and so I should have reminded you that the topologicalness of network charge, how it can come, and so that's also a well-known story. So if you have two surface, and one is the deformation of the other, the continuous deformation of the other, then the difference, so this is difference of network charge. Network charge measured along the first surface and the second surface, and that's of course because by the Stokes theorem B d star j. But this is 0 by the conservation law. So this is 0. Okay, so I mean I can use this conservation law as long as this V does not include any local operator. I mean charged operator, I should have said. Then I can use this. So that's the usual derivation for the topologicalness for the U1. Okay, any question? So if not, I start talking about the generalized symmetry. Okay, so far I've been claiming that conventional symmetry is corresponded to codimension 1 invertible topological operator. Okay, so okay, so today I have colored the chalks, that's nice. So okay, so to generalize, so in this viewpoint, to generalize the symmetry, of course, it's what we do is to relaxing these conditions. So first relaxation that historically done was to drop this. So that's called a P form or higher symmetry. And that like codimension is P plus 1, but still invertible topological operator. Okay. So this is done by Kapustin, Zerberg-Billet. Sorry, I said Gaiotto. I should have. So sorry. Gaiotto, Kapustin, Zerberg-Billet. And sorry. Gaiotto. And okay, so what's this? So first, this the conventional symmetry in this terminology is zero form symmetry. And for higher, so zero form symmetry in many cases acts on local operators. And P, so this acts on so P form symmetry acts in usual case acts on dimension P operator. Okay. And so this fact is comes from just the dimensionality of the topological operator. So in here, if you have local operator, I mean, if you have this codimension 1 operator, codimension 1, then it can encircle local operator. So that this is a natural action that the zero form symmetry can do. On the other hand, if you have codimension P something operator, then what can this operator act on? What kind of operator this can act? And so, okay, for local operator, this operator cannot act because it has too high codimension, so it cannot encircle the local operator. So the natural thing is the dimension P operator. Then in the ambient space, this codimension P and dimension P. Sorry, I said something codimension P plus 1. Codimension P plus 1 and dimension P operator can braid. Okay, in this way. Okay, so this is the natural form of action of a P form symmetry. So one good example. Is the magnetic one-hole symmetry in Maxwell or QED. Okay. So these theories, so just a U1 gauge theory, with or without matter, and okay, so these have U1 one form symmetry. Okay, and so I use the notation that to indicate P or P form, I put number here in the on the shoulder of a group and put the P inside the parentheses. Okay, so this is one U1 one form symmetry, and particularly the magnetic one. The magnetic one, the corresponding, so similar to the conventional case, for each element of U1, we have magnetic one-hole symmetry operator. Okay, so this time, so this is P equals to 1. So this time we have codimension 2. In 4D, it's also dimension 2. And that can simply defined by this equation. Okay, and so just parallel to what I wrote here, I guess, the topologicalness comes from in this case the conservation law is nothing but the Bianchi. Okay, so it's trivially satisfied. Okay, and Yes. Oh. So something is wrong. Yeah. No, 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 no. So I'm talking about. Sorry about. Let me say 4D. So depends on this is this the form for the magnetic operator. This form depends on is actually D minus. Uh, thanks. D minus 3. Sorry. Maybe I can do this. Sorry, I correct. Thanks. D minus 3. D minus, I said something wrong. D minus 2 here. And no. So I'm totally confused. Let me back up. So well, let me do 4D. I'm really bad at this kind of thing. So 4D this is fine. I think yeah, this is F is always two form, right? So yeah. Okay, the confusion is I'm writing codimension here. So I believe this is correct. So D minus 3. So this is D minus 2 general and D minus 2. So codimension D minus 2. So dimension 2 and you can integrate it. Sorry. Yes. Sorry. So yes. So what kind of operator this can this act on? And that's a magnetic thing. That's why I call it magnetic symmetry. So in D equals to 4, it is the fifth line. Which is the world line of probe monopole. Okay, so if you put this U alpha sigma 2 to be inside the space, then the integral of f is just this in space. This measures magnetic flux through sigma 2. It's literally just a B, and okay, so obviously this if you shrink down this operator toward the yellow line, you get the original line, but you get the phase here, and that is this, where M is the magnetic charge of this fifth line. Okay. And so for free Maxwell, there is also the electric counterpart, because there's an electromagnetic duality, and which counts the Wilson line. Okay. Good. That's an example. And okay. So any question or correction? then so there is another way of relaxing this is to relax this word. And so yeah, and when we say non-invertible symmetry, we sometimes refer that imply that it's codimension 1, or sometimes we also drop this condition. So that depends on context. And okay, so that's yet another kind of generalization. Okay, so invertibility means that if you have an operator, topological operator, then there is its inverse, so that u inverse equals u inverse u equals to 1, where 1 is a trivial operator. And here the multiplication is a fusion. Maybe just bring the topological operator in parallel and stack on top with each other. Okay, and this inverse is also obtained by just reversing the orientation. Okay, so now non-invertible. Oh, sorry, and this implies the group-like fusion, which means that if you have more general fusion, maybe I call it, well, G1, G2. So there should be some group, and the multiplication fusion occurs according to the group multiplication law. Okay, so from here to here, it can be shown. Now, I kicked blue chalk. So for non-invertible symmetry, what happens is that you have an operator, and you can always reverse the orientation. So you always have something like an inverse, but not quite. So it's called dual. Well, so I should write this, and this dual operator is defined by reversing the original operator, reversing the orientation of original operator. Okay. So they are always a dual. And what happens when you fuse the two, in most general case, is that you still have a factor of 1, but in general you can have some other thing. So And so this is a non-invertible ness, and so if you have this kind of non-invertible operator, namely its DL is not quite an inverse, then for more general fusion rule looks like this. So you fuse two, and you do not get just a single operator, but you get a sum. And the sum of the extended operator is a bit unusual, maybe, but it's really just defined by like U1 sum is in the correlation function. The sum is just defined by sum of correlation function. Okay. And this Nijk is called the fusion coefficient. These are topological operators. I'm talking about topological operator. Oh no. So that does not happen. So like here. So topological a priori just means that you can deform like this, but yeah. So when you do merge, so here, so if you have the orientation of this and reverse, to annihilate this, you have to merge here to like maybe like this. But this is not in general true, and what can happen is that you have a reminiscent line connecting when you do this merge, partial merge. So here so there are, I mean, generally just some of the lines, multiple lines. Okay, so that's what happens.
So, but in this drawing, I mean, this straight line that you drew, I mean, that can still be made as a arbitrarily small, right? The remnant that you are talking about.
So sorry. Just a second.
The remnant, yeah, the small straight line joining the half circle.
Oh yeah, so this thing is the sum of these. So actually, this is a sum over the line here, and that sum is over the this.
Yeah, but
fusion
that I'm
according
asking
to
that,
fusion.
like, can the contribution be made arbitrarily small?
Yeah, you can make this arbitrarily small, but to evaluate, you would do this segment to be bigger. So at the end of the day, you get some some over the lines.
I see.
Yeah, I should use the different color. So you get here.
And another question was, so you define in this context this U bar, which is what you are calling the dual.
Yeah.
So is it, given a U, is it unique?
Dual is unique. Yes. Dual itself is unique. It's defined by the
one
reversing
plus
the orientation. So yes.
Yeah, so this 1 plus dot dot dot. So can I have another U bar which has 1 plus some other dot dot dot?
Oh, can I have, so is it possible, so is the question that itself can happen here? That's in general, yes. In general, itself can happen here. Yeah, there is a Fibonacci thing. So, and W bar equals to W. One example that I'm not going to talk about is Fibonacci. Fibonacci line have a fusion rule of this kind. So that can happen.
Okay. Thank you.
Okay.
So the support of the topological operator is always orientable or not?
Oh, so here, okay. So here, I require that this this thing is oriented. So the support of the
Always orientable.
yeah, but you can put this manifold on sorry, this topological operator on unoriented manifold if your operator is self-dual. So u is equals to u bar. Then you can use that property to put that operator on unoriented manifold.
Okay, thank you.
Okay. So sorry, somehow my iPad is locked. Oh yeah, so I have to. So this kind of general topological operator has been known for decades in 1 plus 1D. So RCFT context and found by Faraday, and so here the 1 plus 1D RCFT on some chiral algebra. There's a primaries. So this contains, sorry, so let me talk about diagonal RCFT. Diagonal means that the torus partition function is just a sum over the absolute value squared of characters. And okay, so what Faraday found is that for each primary, so this is local, non-topological local operator, but there's a corresponding topological line operator. Okay, and this preserving the chiral algebra means that this line acts trivially on the chiral algebra operator and called Faraday line. Oh, by the way, this Faraday is Eric Faraday. Okay, and the fusion rule is, as you imagine, is according to the same fusion coefficient for the primary. So the same as for OI. So those are called Faraday lines, and yeah. So for example, that Fibonacci line can be found in this way in the tricritical Ising model, and the
So all the topology line can be realized at the Berlin line, or there could be another topological line. So I'm asking.
sorry.
So all the topological line are can be constructed by the Berlin line, or there could be other topological line which is not cannot be constructed by.
Oh yeah. So okay. I believe that in this the diagonal RCFT, the chiral algebra preserving topological line is I think classified by Faraday lines. So, however, if your chiral algebra is larger than just a Virasoro, then you can still ask that whether there is a topological line that preserves only the chiral Virasoro and breaks the chiral algebra. Then the question is not effectively rational out of rational context. So then that question is actually very difficult, even for free fermion, and I do not know at this moment how to classify all the Virasoro conserving topological line operators in two-dimensional free field theory. There is a nice paper about the S1 the compact boson. It's a single compact boson, but for just multiple boson of fermion, how to classify this topological line, preserving only Virasoro, is open question. Yes. Yeah.
Representation. Let's see the question.
Representation of what?
Of the primary primary fields. So in other words, actually my question is, if you consider the, for example, log CFT, is there any like sort of correspondence like this?
Okay, so I know nothing about the log CFT, so I can't say anything. I cannot say anything. Yeah, so I'm assuming a lot about the unitarity, and in non-unitary context, many assumptions falls out. So yeah,
Thank you.
Yeah, for log CFT, actually, what I expect is the breakdown of semi-simplicity, and so, well, okay, I stop, but yeah, I do not know. That's an actually interesting question to study such cases, I guess. Okay, and so let me briefly explain that the Faraday line. So the point is way more modern view of this thing is to reconsider this diagonal RCFT as a Chern-Simon theory on interval, 3D Chern-Simon theory. So according to Witten, this RCFT can be thought as a 3D Chern-Simon theory on interval, and there is a canonical boundary condition for this dynamical boundary condition of this Chern-Simon theory. Okay, and when you squash this interval, you get RCFT. And in 3D Chern-Simon theory, you have Wilson line. So this are Wilson line, this which is topological because the transformer theory is topological. Now this primary is realized by a Wilson line stretching along the interval. So this is primary, but you can also think about Wilson line going perpendicular to the interval and therefore going parallel to your two-dimensional space. And that this after shrinking this interval gives you the topological line. Okay. So from this viewpoint, it's obvious that the two obeys the same fusion rule. Okay. Okay, so this is a well-known 1 + 1D story, but recently we are finding many examples of non-invertible symmetry. In the greater than 2. And how are we doing it? So there are many ways, but in this lecture, I like to introduce 2 methods in constructing or finding non-invertible symmetry in higher dimensions. And yeah, because this story about RCFT is very special to RCFT and does not necessarily uplift to higher dimensions, so we have to find something else. So first method I'd like to introduce today is half space gauging, and the second thing is stacking TKFT. Okay, there are others. For example, I'm not going to talk about it, but for example, is a gauging non-Abelian finite symmetry. But not so many actually. So there are long list, but there are huge overlap. So yeah.
Excuse me, there is a question from the online audience.
Yes.
So the question is, do non-invertible operators always come from invertible operators in a higher dimensional theory?
Sorry, sorry. The question is what? Oh, so here, sorry. I should have emphasized that these Wilson lines are not invertible on itself. So this is coming from non-invertible line coming from the non-invertible line in higher dimensions. So that's one thing, and yeah, and this story does not generalize to higher dimensions. In sorry, it does generalize in some way, but very weak form. So yeah. Yeah. Okay. So there's a story about symmetry TFT, and one can always regard this topological operator in a QFT as a topological operator living on the TQFT topological QFT in one higher dimensions. So there's a story about that. Okay. Yes.
So if the Wilson line is not vertical but has some angle, then what happens when you shrink the region?
So line like this.
Yeah. Right. Yeah.
But anyway, I mean, if this line ends on the boundaries, then it will. So if this line is like this, then after shrinking, what you get is something like this. So okay, so some operator like, so this becomes like this. So to be precise, I should have said that this thing corresponds to the non-holomorphic combination of the primaries. So the product of holomorphic and anti-holomorphic primaries. Here, if you do this, you get something like OI and OI bar is separated in your 2D spacetime and connected by topological line. That's what you get.
Okay, thank you.
Good question.
A question. What changes for the non-diagonal RCFT?
So for non-diagonal RCFT, so the corresponding picture for this non-diagonal RCFT there's also a generalization of 3D picture. Here you have so this is 3D Chern-Simons theory in between, but you insert this topological surface, which in itself invertible or non-invertible zero-form symmetry of this Chern-Simons theory in between. Okay, then so it's known that the classification of non-diagonal modular invariant, I mean CFT, and it is one-to-one corresponding to classification of topological surface in this Chern-Simons theory. So then, I mean, an operator, this OI or J bar, your local operator in 2D is something like this. So the Wilson line, but it pierces through the topological surface, so it might be a junction with a different Wilson line, like this. Okay, so that's here, and then you have topological lines in 2D. That's like might be the Wilson line put on left side or right side, or maybe there's a topological line trapped on the topological surface.
Do you mean the number of topological line operators are more than the number of extended primaries in the non-diagonal case?
Okay, so rough estimate, yes. Yes.
I see. Thanks.
So in this non-diagonal picture, do we have always the same TQFTs on both sides, or we can have different TQFTs one side?
So do you have what?
Different TQFTs?
Oh, here you can have. Let me think. So here I was talking about the case that the chiral algebra is the same for the left mover and right mover. You can, yes, so you can either say that for the case that the chiral algebra are different from left and right side, you can say that yes, so this is a topological interface between two different Chern-Simons theory. That's one way of saying it, yes.
Thank you.
Yes. Okay. Okay, so I'd like to introduce this thing, the half-space gauging construction of non-invertible symmetry. Okay, so here, okay, so the point of this method is that it can be generalizable. It is generalizable to higher dimensions. But as an example, I just do 1 plus 1D Ising model, critical Ising model. Okay, and for the critical Ising model, of course, it is on RCFT. So we do know the Ferranti lines, and I'm going to reproduce those Ferranti lines in different way. Okay, so but more generally, so this is my prime example. More generally, it can sorry. Well, I skip this part. But so before, okay. So this Ising model have Z2 symmetry, that usual spin flipping symmetry, and I claim that so the rough story is that critical Ising model, and you can gauge the Z2 symmetry, but only on this half of your space-time. Okay, and then we use the fact, this is called the Kramers-Wagner duality, and this is where the criticality is important. This critical Ising model is self-dual under gauging Z2, so this is actually isomorphic to critical Ising model itself. Then we get some, so this is topological, and we get some topological line inside critical Ising model. Okay, and more generally, if you have some theory, not necessarily 2 dimensions, acted by finite group, then you can always construct a topological surface in the way I'm going to explain. Okay, and at this stage, in most cases, this T and T over G is not the same theory. But if this T over G and T are isomorphic, which is very non-trivial statement, but if this holds, then we get the topological line, non-invertible. Well, the non-invertible symmetry.
So you are taking two steps. First gauging, then you do additional symmetry operation to come back to the original theory.
So this is not. This is invoking the fact, non-trivial fact that I'm going to explain, but about the system. This part, that constructing gauging on the half space, can be done universally. So you always have a topological interface between T and T over G. Then it might happen to for this to be equals or isomorphic to T.
Oh, okay, so it's like an Ising model. G2 gauging is related to high temperature, low temperature. But at the critical temperature, again, there is additional symmetry. Or for the case, you have S duality wall. And discrete gauging, then you at critical coupling constant, you have additional S duality.
That's exactly what I'm going to talk about. Thanks. Okay. So
excuse me. In this case, how do you know that the line is topological?
Oh, so I'm constructing this interface as a in the way that the topologicalness is manifest. So I haven't explained why this is topological, but I'm doing.
Well,
let me
ask. Yeah, it's basic question maybe. What do you mean by gauging the G2 symmetry? Is it just identifying at each point, or just?
I'm explaining it in right away. Yes. So I'd like to explain first what does it mean to gauge a finite symmetry, or that's in 1+1. It's nothing but so-called orbifolding. But I'd like to introduce it in a modern way, and bit unconventional, but modern way. So one way of introducing the discrete gauging is to introduce a discrete gauge field, and then path integrate over it. But I'm not going to do that. That might be more familiar to some of you, but I'm going to do the in another way, and that is algebra operator. So we are algebra operator. So what to do is first consider, here this situation I be general. So I have theory acted by G. Then I define algebra operator. Okay, so I have invertible topological operator for each element of the group. I define algebra operator A as a sum over the group element and summing this topological operator. Okay. So this is our algebra operator, and so here, sorry, I should assume this is a finite. Sorry, yeah, I should set. Okay, so this is so-called non-simple topological operator. That's because it's a sum of some basic thing. And as I said, this sum of the topological operator is defined, just the correlation function is summed up. Okay. And I'm saying that this is an algebra because there's a multiplication. So there's a multiplication junction. Which is 2 A's coming and A is out. Also, I should have said about the junction. So before talking about this diagram, so I should have said for the simple line, I mean these UGs, I said this fuses according to the group row, but I can also fuse only part of it. So then what I get, so if I fuse this part, but leaving these two, the bottom side with apart, then I get this junction. There's a unique junction. Yeah. Okay. So this is junction. Now, so I define the junction among these UGs in this way. So just fusing a part of the topological operators. Okay, and for A, which is just a sum over UGs, it's just sum over However, here I have a room to put the number here. So I put this. This is just a number, I mean function. No, So this is called a multiplication because I bringing two operators and fusing into the itself with some. So this should be thought as like multiplication in the group algebra, and with but this multiplication is twisted by some number. Oh, so yeah, so okay, so this fuses. Okay, the way we should regard this as these two are A's because we are summing up. Here, of course, here, yeah. So this does not exactly equals to A. However, so how we should think about is that each summand is inside this is A. So summand of A, and by that so I'm skipping all the formulation of the of fusion category, so it's a bit confusing. Yes, but yeah, the point is that by fusing this, every time fusing the two, we get UG1 G2, which always appears in A itself by construction. So this includes the normalization constant. Yes. So by this, like oh yeah. So what I demand is that associativity which is mu equals to mu. And if you can find this epsilon such that this is satisfied, then you can regard this as a 3-to-1 scattering, and how you resolve it does not matter. Okay, so there's two ways of resolving 3-to-1, but I demand this multiplication be associative. In other words, this junction should be unique and independent of how you resolve this 3-to-1. Okay, so this is an anomaly-free condition. Okay. Yes. So yeah, as a remark, so this, well, yeah, okay, I don't see it now. Yes.
Sorry, I was asking what exactly is the anomaly free condition and why is that? Can you explain that again?
Oh, so yeah, I'm going to say that why this is this does corresponds to anomaly free condition. But yeah, so this let me explain in a bit later. Yes. So what to do? To define gauging, what we do is, so before that I also have to define the co-multiplication. Sorry. So co-multiplication is just A comes out and split into two A's. So this is just comes like UG1 G2 splits into UG1 UG2. So I should clarify what I mean by this summation symbol. So by representing an example. So let's say and I do not put our number here, and that's a kind of a gauge fixing condition. I can move this part of epsilon to here and there, but I choose this. That's a technical point. Okay, so like using these junctions, I can draw something like this, and that's like so each A is summation over G's. Okay, so G1, G2, G3, I don't know, G4, G5, G6. So we are summing over G1 to G6. So each are the runs over the group elements of the group. But here, this of course, the junction is valid only when the three group elements are consistent in terms of the multiplication. So this is consistent. Yeah. So okay. Another way of answering the SOC question is maybe we can say that this is summing over G3, but whenever this G1, G2, G3 is not G1 times G2, this number should be 0. That's another way of saying it. Yeah. So that's probably better. So maybe I also do that. And here delta G1, G2, G3. That's better. Okay. So here I just consistent sum over the consistent assignment and also maybe I put the epsilons here and okay, and I also demand the speciality. I mean, this is just a normalization. But this is again technical point. But A equals to. So you can remove this kind of bubble, and this can be achieved by renormalizing epsilon there. So this is not the additional condition, but just a normalization. Okay. So given this, what to do to define the gauging? I'm introducing this machinery to define gauging, discrete gauging, and gauging it can be done by inserting mesh of A. Here, mesh of A is, well, literally just a mesh of A. So say you have some Riemann surface, then I should have said this is a fine enough mesh of A. So something like that. like this. Okay. And everything are A's, and you put mu or delta at each junctions, and blah blah. So I should, well, this doesn't matter, but here and okay. So that's your so the partition function. So given this algebra and satisfying this condition, the partition function of gauge theory is defined by partition function of original theory with this mesh inserted. And the point of this configuration is that it endures this thing does not depend on the detail of mesh. Okay, so I draw this mesh arbitrarily, but the detailed form does not matter, and that's basically because if this equation holds, the associativity holds, then we can always change the form of mesh arbitrarily as far as it is fine enough. Okay, so it does not depend on detail of mesh. Okay, so that's the definition. And so for torus, what happens? So torus, you can have a mesh like A here mu delta and this. And this is fine enough. Roughly speaking, it wraps both cycles. That's fine. And so what it is. So because it's associative, so we can regard this as just G1 and G2. G1, G2. G1 commutes with G2. Well, okay, that's fine. And epsilon G1, G2. Okay. So this is nothing but what you find in, say, Polchinski, in defining the orbifold partition function. But this number is called discrete torsion in the old context. Anyway, and that's a generalization. So okay, but then I'm introducing this machinery so that I can do gauging on not the whole space, but on a subspace of the manifold. And okay, so is this clear to you? Yes, please.
Yes, I just wanted to make sure some of things. So because the algebra operator is defined as a sum of all UG, so you're necessarily summing over all possible discrete gauge configurations.
Yes.
And epsilon takes care of different topological structures of the
epsilon,
mesh, or
epsilon is some choice. This is like a theta angle.
Yes, that's what I mentioned, topological sector thing.
Yes. Yes.
Okay, so in principle, you can have a different mesh which can be topologically distinct each other, or a given single mesh already includes different topological structures in it.
So this multiplication map already, so this epsilon already encodes the theta angle. This is
got it.
Theta angle. Yes. So fine enough mesh involves all the possible topological sectors, and yeah, and this epsilon gives you the weight to each topological sector. Thanks.
Thank you.
Yes. Okay. So that's So this is a modern viewpoint, but then so advantage of this viewpoint is that you can define a gauging on a subspace of the space-time, not only on the whole space, and so before maybe before going to that, one comment. Sorry. Okay, I write here. One comment is that this algebra, the concept of algebra, and its gauging, I mean mesh, can be generalized to non-invertible case. So there, you should find some A. So here I've been talking about start from the just finite invertible symmetry, usual conventional symmetry. But if you already have non-invertible symmetry, then you can also try to find some non-simple topological operator, some sum over your invertible or non-invertible lines, and try to find some mu, the multiplication junction that satisfies this condition. And in higher dimensions, actually you have to. Oh, sorry. So that condition I wrote is about the 1 plus 1D. And higher dimensions, the condition differs. But okay. But something like this. So you still try to find this associative algebra inside your non-invertible symmetry. And then once you get this with additional conditions, you can define the gauging of a part of this algebra inside your non-invertible symmetry. So I'm not going into detail of this story, but there's a notion of gauging of a part of non-invertible symmetry. Okay, so that's a comment. Then I talk about half space. Should I stop? Okay. Then I stop. Yes. Sorry.
Yeah. Last thing. Yeah. So, do you have any questions? Yeah.
I have a general question. In geometrical engineering, non-invertible symmetries correspond to what property of Calabi-Yau?
So geometrical engineering, and is the question is how the non-invertible symmetry is realized in geometrical engineering? Is that the question?
Yeah, in geometry engineering, non-invertible symmetry corresponds to what property of Calabi-Yau?
So there's a nice works about that by many groups. So I do not cite any so that I don't miss anyone. I miss all, and so but yeah, there are different works on that. So here, so in geometric engineering context, it is proposed that these topological operators corresponds to the d-branes living at this infinity of your cone of say Calabi-Yau or something, and then that's the property of invertibility, non-invertibility is coming from the property of the branes, wrapping some cycles at infinity. Yes, I do not know the detail, but yes, that should be the idea.
Okay, thank you.
Hi, thanks for the great lecture. I just wanted to make sure if I understand the anomaly-free part. So your last drawing, I think, clarifies in the sense that I think none of the UGs you included it as a part of the operator A has mixed tooth anomaly when you try to change the order of operation. Is that correct?
Sorry. So the equation is this?
Right. So basically, you want to exchange order of the two operator in that drawing, right? And once you have a mixed tooth anomalies, you will pick up the phase. But then the fact that you demand that is exactly true with phase one, I guess means that none of the topological operator has a mixed anomaly, tooth anomaly.
Oh, yeah. So yes. So this thing.
In other words, if your G1, G2 had a mixed tooth anomaly, and when you try to change the order of the G and G2 to go to the right, it will pick up the phase, right? So
in general, this picks up a phase.
Exactly. Okay.
Yeah.
And so basically, you demand that you don't have a tooth anomaly, and then you can then construct the gauging of those.
Yes.
Okay, makes sense. Thank you.
This is on. So the most basic case is a Z2, then this, and so for Z2 there's only the trivial and non-trivial line, and naively you can do, you might think that you can do this recombination, but there can be a phase. This is on.
Yeah. So I have a question.
Yes.
So you introduced this algebra like operator. So I'm wondering what's special about this object. So it looks like a center of the group algebra, for example. So
yes, this is really just a group algebra, and yeah. So one good thing is to allow us to generalize the notion of gauging into the non-invertible case. That's one good thing. The other thing is that this notion of algebra is useful to define the gauging on a subspace of in the entire time space-time, and that's what I'm going to talk about. That's yeah. Well, that can be done in the alternative way of introducing finite gauge field, but at least historically, this is how it was found in the condensed matter literature.
So
more close to.
So mathematically, does it have some special meaning?
Sorry.
Mathematically.
Mathematically, what?
Does it have some special meaning?
Oh, mathematically, this is very, very important concept inside the fusion category. So this is the algebra object inside the fusion category, and that's very important mathematically.
I see. Okay. Yeah. Thank you.
Yes.
Any other questions? Yeah, I have a question. So in your definition of fusion coefficient is defined as some relation between the correlation function of this topological defect. So from that definition, is it obvious that these are the integers?
Oh, so from that definition, it's okay. So it has to be integers. That's because of so it's not just about the numbers, but also vector space. That's the point. So you can think about fusion on the pair of points for example. So U1, U2. And this is like in general IJK, maybe IJ, IJK, UK. Now you have here the Hilbert space twisted by this topological line. So you quantize your field, but with the time-like insertion of some defect here, and you also have the same. And here you get the sum. This is S1, so you should get sum over. Oh, sorry, I said no. Sorry, this is not necessary. Sorry, let me start over. Sorry. So this is better. So okay. So I can define a Hilbert space insertion of two lines or operators. Okay, so you contact your field with time-like insertion of topological operators. Then, okay, so then after fusing, it's some Nijk UK. Okay, so then this Hilbert space is direct sum with this coefficient. So because this should hold on after taking trace, so it has to be like the coefficient here is integer, so that this direct sum makes sense. So that's
Yeah. Any other questions?
That's
Yeah.
okay.
If not, let's thank the Kantaro.
Thanks.
Again. So we will resume at 10:50. Yeah, who lost this with what? AirPod? The speaker, one of speakers?
Nice to meet you.
아이팟이라고 부르잖아 이거.
이거 어제 주운 거예요?
강의실에 있었어.
강의실에
어제
있었어요?
어떤 사람이 나갈 때 강의 끝나고 바닥에 뭐 주웠다고. 그러니까.
Anyone lost AirPod?
But he didn't show up yet. Then he cannot hear you.
Maybe.
Hi everyone. Let's start the second session of the Tuesday. Now this is the last lecture, lecture 4 of the triage. Yeah, please start.
Okay, thank you very much. So before I start, or well, not start, but continue with the topic of the previous lecture, I wanted to make some comments related to some things that were said in Francesco's lecture, and also that I was asked after my second lecture. So I want to go back just for a minute to these universal studies of JT with matter at largest knot but finite temperature from the first 2 lectures, where is not a exact model, but what I did was to solve this model at essentially infinite knot but finite temperature. And the gravity path integral gives a black hole spectrum near extremality that has this funny behavior, where the dashed line is the semi-classical answer, and the green line is the quantum corrected one that goes to 0 at this gap scale of order 1/c, that is not really a gap. And C comes from the boundary conditions of the dilaton, or it's a parameter that has to be computed from matching the ADS2 throat to the higher dimensional black hole. Conformal symmetry is lost at these scales. And e to the s naught, or the exponential of the extremal area, is not really an extremal entropy, but at most related to what Seok was asking, can perhaps be interpreted as computing the number of black hole states in a window of order 1/c. And we expect non-perturbative gaps, which is the topic of the last 2 lectures, of order e to the minus s naught, that cannot be seen perturbatively. In particular, they are exponentially suppressed in 1/g Newton. And this is impossible to analyze in the more realistic models of JT with matter, but we'll be studying the toy models. But the comment I wanted to make is that this is definitely not the spectrum that appeared in Francesco's talk about black holes in ADS5. And the reason is that they preserve some supersymmetry. The conclusions that I mentioned before are drastically modified. So the reason why I didn't present this analysis is it would have taken me a while, because when you have supersymmetry there, so the first thing I didn't do, that is easy to do, is to go back to this analysis and extend it by the presence of gauge fields, even without supersymmetry. So that I didn't do, but it's easy, you can do it. Now the complication in supersymmetry is that you have extra modes from the gravitino, fermionic modes, that introduce interactions between these gauge fields, in particular the one that corresponds to the R symmetry, and the Schwarzschild mode. And then that analysis becomes much more involved. But since perhaps it's important to connect my lectures with Francesco, I wanted to at least emphasize again that when you repeat this analysis for supersymmetric black holes, then the density of states looks something like this, where it goes to 0 at some gap scale of order 1/c, and then it has a big delta function at exact extremality, and the coefficient of this delta function is precisely proportional to the exponential of this parameter S naught. And this picture you only get in a sector of fixed R charge that is 0, this superconformal R charge. If you look at the sector with a different R charge, then actually the picture, even in supersymmetric theories, looks closer to the non-supersymmetric ones. And that's what Francesco was explaining related to why the index is the same as the degeneracy. And this is the situation when the extremal black hole preserves 2 supercharges, that is called n=2 JT, and appears in the throat of the black hole that were studied. The case with, this should be n=4, sorry. The case with 4 supercharges, n=4 JT, appears for black holes in flat space, which normally preserve 4 supercharges. For example, for example, the n=2 supergravity in 4 dimensions. And in this case, conformal symmetry is restored, because thanks to this gap that is available perturbatively, you can take temperatures to be much smaller than this gap scale, and then you'll just pick up this delta function, and a conformal theory in 1 dimension is just a topological theory of ground states, and that's what we are reproducing. But again, as opposed to the previous case, this gap can be understood in perturbation theory. The gap is of order G Newton, and not exponentially small. And this means that this delta function of these states can be interpreted as extremal black holes, which is what Francesco was counting. But in this case, presumably if you go to the ground state of this system and there is some exponentially small gap, it cannot really be interpreted as a black hole anymore. It's some some mess of non-perturbative effects. So there are not really extremal black holes that are not supersymmetric, but there are that are supersymmetric. And computing this was the topic of the other lectures. Okay, before I move on to the topic of this lecture, is there any question? Yeah.
Newton constant instead of something depending on the charge?
Oh yeah. I just wanted to write it. So this number here would depend on the charge.
Okay.
But I'm imagining that. Oh yeah, sorry. Maybe I used a different notation convention before, where I said G Newton to 1 and I take large charges. Yeah, you're right. I just wanted to emphasize that this is independent of the particular case of Reister-Nordstrom that I wrote before. But in general, the important thing is that it scales with G Newton. And
yeah, maybe it'll be too tough question, but do you have any insights on the field theory dual interpretation of the gap?
Of this gap?
Yeah.
No. That would be amazing to understand it in for black holes in ADS. There is some interpretation for black holes in flat space, like in the D1, D5. There was before all this was understood, like long time ago, there was a paper by Maldacena and Saskin where they interpret, but they computed that weak coupling, so it's not obvious that the argument still works at strong coupling when the brains become black holes. But
Maldacena-Saskin means really long ago.
Yeah. So
late mid-90s or something.
Yeah, so they were doing some calculation at weak coupling and interpreted it in terms of the black hole spectrum. That is, but the way they think about it is that the black hole states is counting strings in this D1, D5 system. And the gap comes from the lowest excited state of the string that is wrapped in the in this large circle where the D1 brain is. So this is the low. So this gap is related to the lowest excitation energy of that string. That's one physical explanation they give.
So the result, I guess, is similar for n equals 4 JT, I guess.
Oh yeah. Sorry, that the result is for n equals 4. Yeah.
Okay, thank you.
Yes, but there is not really any argument at strong coupling. But the good thing about the D1, D5 is that it's described by ADS3 CFT2, and then you can argue that you have this gap from Virasoro symmetry. So you didn't even need that argument. But in the case of n equals 4 Supergiant Mills or black holes in ADS, there is no argument based on the just on the CFT symmetries that would tell you that there should be such a gap. So then it becomes much more non-trivial. Yeah. Any other question? Okay, so I will go back to the topic of this lecture where we forget about where the ADS2 came from, we neglect matter and work with this toy model that is pure JT gravity. If you remember from a couple of days ago, I presented the solution of pure JT gravity, and what I was doing was building up to describing what the dual is by introducing random matrix theory for the GOE ensemble. And the point where we left out, I think this slide is just copy-pasted from the last slide of the previous lecture. We found that in large L limit, large number of eigenvalues of this quantum system, described by Hamiltonian, the matrix integral is controlled by a saddle point for this density of states. That is a solution of this complicated equation, and I gave the solution for the Gaussian matrix potential, that is this Wigner semicircle. And again, it has this finite extent, A, that is related to the, you can think of this as a Toft coupling of this matrix integral. So at finite Toft coupling, the one-cut density of states has a finite range. And one can do similar, solve more complicated matrix potentials. There is a nice way to solve this type of equations with the resolvent method. Now, what I want to explain next is what is the double scaling limit of the matrix integral, because in particular, density of states like this does not look like JT, which has this form. Particularly, it goes all the way to infinity. So we need somehow to modify the matrix potential to reproduce that feature to leading order. And this is what's called the double scaling limit. It's a limit of matrix integrals where the size of the matrix goes to infinity, because if the extent of the density of states goes to infinity, then there is an infinite number of eigenvalues. And the toughest expansion is in L gets replaced by a new parameter S naught, which I call S naught because it will become the S naught of pure JT gravity. But for now, just think of it as a parameter in the matrix integral that I'm about to introduce. The limit will be constructed in the following way, such that it accommodates density of states with arbitrarily large energies. And the new parameter appears in the such that the following limit works. So in general rho, the density of states is given by L, the number of eigenvalues, times some order 1 number. And this order 1 number is a function of energies, and the normalization is fixed such that the total number of eigenvalues is L. And what we want to do is we want to take a limit where L goes to infinity. The extent of the length of the cut, this parameter A, also goes to infinity, but the density of states remains finite and proportional to this parameter e to the S naught, which we will take to be large. So we are taking A to infinity, L to infinity, but keeping the leading order density of states finite. And that's what the double scaling limit is. Of course, we will also take this, even though this is finite S naught, we will also take it to be large to allow for a topological expansion. But once we take this double scaling limit, L disappeared completely. It's just infinite, while S naught is large but finite. So with more complicated matrix potentials, we can create density of states that, before we take the double scaling limit, would look like this, for example. And then we take A to infinity and we zoom in this region. And now we can create double scale matrix models that to leading order have density of states that look like this. And now e to the S naught does not become the number of eigenvalues anymore because that's infinite. But e to the S naught you can think as some average level spacing of the eigenvalues within each particular realization of the matrix. So it's an expansion at large or at small gaps between the energy levels. Yeah.
So maybe I missed something, but why is not a limit on the semicircle? I mean, if you're taking a double scaling limit of the semicircle, why do you get a more general shape and not just a larger semicircle?
Because the point of this picture was to match with JT. And then if you do it, I'm going to show you in the next slide, with a semicircle, you'll get a square root edge. But I want to reproduce the whole sinh of square root E of the JT gravity. I want to reproduce the whole disk density of states of the Schwarzschild.
Okay.
And then I need to add extra terms to.
Oh, I see. So you're gonna change the potential. So it's
yeah,
no longer the potential that give you the semicircle.
I want to reproduce this whole curve to leading order, and what you're saying would just give you this edge.
Okay.
Yeah. Okay. Any other question?
If you just know the density of states of the JT theory, can you if you just you know the leading density of states that is obtained in the JT theory, right?
Yeah.
But is there a unique matrix model that will give in the double scaling limit that particular density of states, or
no? Okay. No. For example, it depends on how you regulate this double scaling limit.
Okay.
Yeah. So this is a choice you have to make, but after you make that choice, then this it's a non-trivial fact that these connected contributions have good limits as A goes to infinity. Yeah, that's a non-trivial fact. Of course, it depends on the temperature, right? Because if you, let's say you try to take a limit where beta is 0, then that will be sensitive to the whole spectrum, also to the large energy part of the spectrum. So you are imagining, I'm imagining that when I take this limit, the temperature is not too large, such that the temperature doesn't scale with A in a way that would make it sensitive to the edge of the spectrum. The temperature is taken to be order 1 in this limit, and then nothing depends on how you regulate it. Yeah.
So is there any parameter in the matrix model that could potentially generate the gap if you tune it? Like it moves the endpoint of this cut, the support of the density?
Yeah, so unfortunately, you could study n equals 2 pure JT gravity. I guess that's what you're asking, and how to reproduce the gap. No one found the matrix model dual of pure n equals 2 JT gravity. So yeah, I don't know. That would be nice to. It would be nice to know. I mean, if you have a gap, you can just put it. Like you could just assume, oh, it's just the GUE, and I put the gap by hand, and then I put a delta function by hand. But that's not. That wouldn't work with the in the genus expansion. It will give you the wrong answer. So there is something. Well, this will become clear later, but there is something that you put by hand, which is pick the matrix potential to reproduce the leading order density of states, and there is something that has to be proven, which is that order by order in the genus expansion, everything will match once you make that initial choice. Yeah. And that would not work if you just do that.
I have some speculative question.
Okay.
So, in the random matrix theory, there is some statistics of the lowest eigenvalue. I forgot the name. Some distribution. You know, the distribution of the
Tracy
lowest. Tracy,
wisdom.
Yeah. SYK model, it was a little bit not sure because I think Lagos paper, but in this JT gravity, can you also study such kind of lowest distribution of the lowest eigenvalue, or maybe it's not possible to see?
Yeah, I think maybe that's in a paper of Clifford Johnson, where he uses something called the Fredholm determinant to write down the probability distribution of individual eigenvalues to fall in certain ranges. So you can ask, what is the probability distribution, not of the density of states, but the probability distribution of the lowest eigenvalue for each realization to have a certain value.
From the gravity calculation, or
no, from the matrix model. Yeah,
matrix model.
Yeah. So it's kind of automatic that it will work once you. But it's nice to do it anyways.
Thank you.
Yeah. Okay. So let me give you an example that was already mentioned, which is the double scaling limit of the Wigner semicircle. And this is perhaps the more famous example of matrix models. So the upper half is what I described already. This is the Gaussian matrix model with a finite Toft coupling. And then the double scaling limit involves taking A to infinity. And when we take A to infinity, this square root becomes just the square root of E. I think there is a typo here. I wrote it in different. Okay, sorry. The argument of the square root should be this instead. Okay, sorry. I think I copied it from a different place. So it's a square root of. Okay, let me. Sorry. So let's look here. If I take A to infinity, then the argument of the square root becomes just E, right? Okay, then let's go back to the other formula and imagine that I didn't mess up this formula. And then here you have the square root of E. Then as you take A to infinity, the density of states will go to 0 if you don't scale L as well. So in the double scaling limit, you take L to infinity such that this combination, L over A to the 3/2, is kept fixed and equal to S naught, E to the S naught. And that's where the E to the S naught comes from. And again, this effectively zooms into the edge of the spectrum here. And the new density of states now is E to the S naught times square root E, right, which looks like this. And the topological expansion now is done in terms of E to the S naught, which is a rescale size of the matrix. And the fact that you need to take L to infinity is clear. I mean, if you have a finite extent, you need an infinite number of eigenvalues. Or in other words, if there are a total number of L eigenvalues in this finite range and you take it to infinity, for the integral to be given by L, the density of states has to go to 0, just by counting eigenvalues. So we need to take this limit for the Toft coupling and also for the size of the matrix. And now we can do exactly the same for JT. So we need to, if we want to compare with the JT density of states, we need to pick a regulated density of states with a finite A. And let's say we pick this one for concreteness. So here I just took the density of states of JT and replaced square root of E by this by a similar factor than what appears in the previous example, and and this is fine. Then I can pick this density of states, and then I will construct the matrix integral by picking a matrix potential, which is whatever I need to produce this as a saddle point. So the matrix potential will look very complicated, but in the end, we want to pick it such that this is true. So here I already rescaled A and L into S naught for convenience. So now we take A to infinity. This becomes square root of E, and we end up with the JT density of states. And here what I didn't write down is how this E to the S naught will be written in terms of L and A, but you can do that exercise. So this has to be proportional to L, and then the proportionality constant is found by demanding that this whole integral, the integral of this function everywhere is equal to L. So now this fixes what the matrix integral is. So to compare with JT gravity, we pick a matrix potential in this limit that finite A has this as its saddle point, but we take A to infinity. Yeah.
It seems that you will be working extremely hard, finding the potential to reproduce the known result. What is this matrix model good for?
That's subleading correct. So that's what I said. So we pick this weird matrix potential to reproduce this function, but then order by order in the genus expansion, the result from the matrix integral and from gravity match. They are exactly the same.
Yeah, but why do you need another independent matrix model formulation to begin with? Can you?
What do you mean by another independent?
I mean, maybe I missed some point in your last lecture, but trying to write down a matrix model version formula for these JT things. I mean, what is good about this new viewpoint? Is it easing the calculation? Or,
so we solved pure JT gravity, and we're trying to find what the holographic dual is.
Oh, it's I see.
And I'm saying that the path integral of pure JT gravity on any surface is computed by a random matrix model, where the random matrix is interpreted as a random Hamiltonian of the dual quantum mechanics.
Okay, thank you, yeah.
And now I'm constructing the ensemble of Hamiltonians that reproduce, that is dual to pure JT gravity.
I see. So you're systematically constructing the boundary theory. Sorry,
yeah. I'm constructing the boundary theory. I have the choice to make, which is what is the disk density of state, but then everything else is automatically determined. And then once I make this choice that I'm making now, all the subleading corrections in the genus expansion have to match, and that's what I'm gonna just say next. Yeah. Thank you.
Need to be fixed to fix the disk density in the matrix.
Well, you could say that it's infinite parameter because it's one function, v of h. Yeah. So I need to pick. I mean, if I'm saying that I'm gonna average over theories, then I need to pick a probability distribution, and that's what the matrix potential is doing. Is picking a particular probability distribution for the theory, for the boundary Hamiltonian. Okay. So once we pick the disk density of states, what do we do? So we want to compute the subleading corrections. Sorry, let me go back. We want to compute all the terms set Gn, which of course I written similarly to the one in gravity because it will be the same. But in principle, this is computed from the matrix integral. So I need to compute the higher genus corrections knowing the matrix potential. And this is done by what's called the loop equations of random matrices. And I don't really know who introduced them. This was way too long ago. I think it was Migdal. I don't know. If you know, tell me. But they're essentially, I'm not going to derive them, but you can think of them as Schwinger-Dyson equations for the random matrix. So similar to what was used yesterday to derive the word identities, you write the matrix integral as an integral over eigenvalues, and you use the fact that the integral is independent of change of variables of the eigenvalues. And the fact that this gives something useful is amazing, but it does. This is the type of relations that you would derive from such an argument. And the point is that, okay, so you can use this argument to derive exact equations, such as this is an example, the one that I wrote here. But now, written this way is completely useless because it's a relation between things that I cannot compute anyways. Here I mean the expectation value of the partition function to all orders in the genus expansion. I don't mean that only the disk one. But this becomes powerful when we take a relation like this and we expand, we do perturbation theory in the topological expansion in e to the s naught. And then these equations become useful, and it gives a recursion relation that allows you to compute all higher genus corrections starting from the leading disk result. And this is sometimes represented diagrammatically. And of course, this is very reminiscent of the pictures I drew last lecture about the Mirzakhani recursion, and that's not a coincidence. Perhaps the best reference that really turned these loop equations into something extremely easy to apply and useful was by Einard and Orantin around 20 years ago. And here what this picture means is that I'm computing the genus G correction. Genus is the genus of the surface that triangulates the Feynman diagrams. I'm not talking about gravity yet. So you compute the genus G correction with some number of boundaries, and the recursion gives it to you in terms of contributions with either lower genus or lower number of boundaries. So then one can show that this is an actual useful recursion relation that can really be used to compute everything else. So I'm not going to derive it, but let me just write it down for you to show you how it looks like. And they're simpler to write in terms of the resolvant, which the resolvant is this object. It's a Laplace transform of the density of states of the partition function. But anyways, just take this as, it's just easier to write in terms of this quantity R of E than in terms of the partition function. And similarly, products of this resolvant have a topological expansion, just like the one for the partition function. And finally, it's useful to write the recursion, it's useful to introduce something called the spectral curve. For that, we define a coordinate C that uniformizes the spectral curve. The spectral curve will have a branch cut where the density of states is non-zero. So this C has two sheets. The spectral curve is a curve in this variable x and y as function of C, such that y is given by the expression of the disk, leading order disk density of state, removing the e to the s naught. This is a further one. So these are just definition, but you can think that the spectral curve is just a function, y of z, where the energy is, the eigenvalue is z squared, and it's the density of states with the e to the s naught stripped off. And then one defines these WGNs, which are the resolvants times these powers of z. And the reason why this is useful to define is that one result of Einar and Orantin is that the loop equations depend only on the spectral curve information and not on, so they're very geometrical about the spectral curve. These are forms on the spectral curve, and one can associate recursion to them independently of the fact that they might come from matrix integrals. Anyways, if one follows this route and derive the density of state, the loop equations, and expanding the genus expansion, this is the final answer. So the resolvant, this rescaled resolvant, where now this uppercase C means all the other n-1 arguments, which are square roots of the energies, is given by a residue of this function that involves resolvants with less genus, with less boundaries, and it depends also on the spectral curve. So one of the useful things about this formula is that it depends on and one of the reasons why I didn't write down for you the matrix potential is that this function, this recursion is totally independent of the matrix potential and depends directly on the disk density of states. So I didn't even need to write it down. I mean, there is some formula, but I don't need to write down what the matrix potential is in order to be able to use this recursion. So that's one of the reasons why it's useful. So once you tell me that you want to find the dual to JT and you tell me what the disk density of states is, matching with the Schwarzschild, then this just determines automatically what the other results are. And just to remind you, or well, just notation, the resolvant for one boundary is given by this function of the disk density of states, and the resolvant with two boundaries is a universal function that is independent of the density of states, and is non-trivial result. But it's true in in both matrix integrals, and it's also true for, well, and JT as a non-trivial result, JT also reproduces this universal answer. And if you're interested in the derivation of this, very nice derivation is in section 4 of this paper, where they, yeah, there is a, yeah. Okay, so just to a little bit more concrete, so we can apply this to the density of states of JT gravity. And sorry, this rho naught should have e to the s naught. But when we translate this to the spectral curve, it gives us a function y of c that is given by this. And the sign appears from the square root, and just it's an analytic continuation in the energy, where the energy is c squared and minus c squared. Yeah, the fact that the sich became a sign is because of this minus sign here. Now, a non-trivial result that was shown by Einar and Orantin as well, shortly after Mirzakhani's result, was that this topological recursion is exactly the same recursion derived by her in terms of the Laplace transform Weil-Peterson volumes. So if I take the resolvant of the matrix integral and I define volumes, I'm not talking about gravity yet, I'm just defining a function that I call volume, which is this VGN through this Laplace transform. So this depends on the energies through C1 to Cn, and this depends on variables B1 to Bn that are Laplace transforms of the energies. If I define this Vn in the matrix model, and I pick the spectral curve to be the JT one, what Einar and Orantin, they didn't phrase it this way, but what they showed is that the recursion relation for these volumes is precisely the same as the Mirzakhani one. Is there any question about this?
Is there an analog of the half trumpet part in this random?
Sorry,
is there a, what is the analog of half trumpet in the gravity here?
Half trumpet. What is a half trumpet?
The full double trumpet, you split it into two pieces and did the B integral in between, right?
Yeah, so that's what that here is what's computing this W0,2.
So W02 is the full.
Because it has genus 0, so there are no handles and there are two boundaries. So
yes, but you computed it using two pieces and then gluing them together.
Oh, so the matrix integral just gives you the final answer, because it doesn't. The matrix integral doesn't know that you decide to do the JT path integral that way.
Okay.
It just gives you the final answer, and then that has to match with the JT gravity final answer.
Okay.
Yeah. Yeah. Yeah.
So just to make sure I understand. So if you go to the next slide.
Yeah.
So you are saying that the connection, let's see, between Mizrakami and topological recursion is valid for this specific spectral curve, a specific disk amplitude, or is more?
No, only for this amplitude. Yeah. For this density of states. Yeah. For this spectral curve. Yeah. So to show that you get, so you have a matrix model, you compute resolvants, and then through this definition, you define what you mean by this VGN. And then you replace it here, and here y of c appears. There is no functional freedom in Mirzakhani, it's just specific recursion. But what they found is if this is this sign of c, comes from JT, then the two recursions match. And there is another paper by Einard where you can ask what happens if you pick a different spectral curve. And he shows that these are different integrals of certain forms in the moduli space. So if I remember, I had some formula where I was writing the Weil-Peterson volume as an integral over the punctual moduli space with e to the Weil-Peterson form plus corrections. That's the definition of Weil-Peterson volume for surfaces with geodesic boundaries. But you can consider more general integrals over moduli space of the punctual Riemann surface with, I don't know, any arbitrary function of this Weil-Peterson form, or also psi classes or tau classes they're called. They're forms on the moduli space. This spectral curve computes the volume, and another spectral curve computes more general integrals over moduli space. Yeah. Yeah. The what?
How to understand the genus and the boundary in a matrix model? Yeah, maybe.
Well, the genus is just the order. So the answer is perturbative in e to the minus s naught, and the genus is just the power. We call it the genus, and the reason why we call it the genus is because this is exactly a Toft limit of the matrix integral. So this is the genus of the surface that the Feynman diagrams are triangulating.
I see. Okay, thank you.
Yeah. But I didn't have to call it genus. I could just call it some, I don't know, perturbative parameter, but of course it matches with the genus of JT gravity. And this is related to some discussion we had in last lecture that the matrix seems to be playing a dual role of triangulating the spacetime, but also as a dual Hamiltonian. Yeah.
So this parameter B is can be understood as some temperature on the boundary, or?
No, this is the geodesic length. So if you, yeah, this is the same as in JT. Is the, oh, you mean if you try to interpret this as some observable in the matrix integral?
No, I mean just like the gravity side is related to the beta in some.
Yeah, on the gravity side, this is the geodesic length of the geodesic boundary, the length of the geodesic boundary. Okay. And again, this is very non-trivial, and I'm not going to derive it in front of you, but this proves exactly the correspondence that we claimed in the beginning, at least to all orders in a perturbative e to the minus s naught expansion. And to answer also your question, in the last lecture, we computed the left-hand side, the gravity path integral of pure JT gravity. On this lecture, we computed I told you how to compute the right-hand side. This result by Einar and Norantin show that the two are exactly the same. So you can interpret the holographic dual of pure JT gravity as this random Hamiltonian with this specific probability distribution. So every time you have a boundary in the gravity path integral, you insert a trace of e to the minus beta h, and then you average over h at the end of the day. No, h you should think of it as the Hamiltonian. Is the Hamiltonian. Yeah, quantum mechanics is a theory with a Hilbert space and a Hamiltonian, and we are averaging over the Hamiltonian. Maybe what you're asking is, so in part because this is just pure JT gravity, there are not really operators that I can insert other than the partition function itself. If I would have operators, then it would be sensitive to how the Hamiltonian is written in terms of those local operators in
yeah, maybe I was trying to naively imagine what are the elementary degrees of freedom of this quantum mechanics, like vector model, matrix fields or whatever. But
no, I think I would say that pure JT gravity is too simple of a theory to see any structure.
Okay.
If you would do a theory with more structure in the bulk, then you will, for example, matter, then you will start to see such a thing.
Okay, thank you.
An example, if we were discussing with Francesco the other day, if you're familiar with the C=1 matrix quantum mechanics, there is theories of 2D gravity that are string theories, and there the matrix is not the Hamiltonian. It's an actual matrix degree of freedom, and the Hamiltonian is given in terms of that matrix, and that's not an ensemble. That's a specific Hamiltonian with a matrix degree of freedom. But then in the bulk, you don't have JT. You have a string theory. That's an example where, yeah. Another question? Okay, so let me show you roughly how this is. I thought instead of trying to argue about the derivation, I would just show you an example. So in the last lecture, if you remember, we computed the contribution to the single black hole partition function with one wormhole. So it's this picture where we have the disk with a handle attached to it. We computed the Weil-Peterson volume using Mirzakhani's recursion. And then we glued the Weil-Peterson volume with the trumpet to compute the partition function. So now I want to show you the calculation looks like using the matrix integral. So if we use the Einar and Norantin loop topological recursion for the specific quantity that we need, that would be the resolvent with genus 1, which then we will turn into the partition function. But let's first compute the resolvent at genus 1 with one boundary. then the complicated equation that I showed before reduces to this simple residue of the resolvent with genus 0 and 2 boundaries. And you can think of this as you take the disk with this handle, and then you just cut the handle in the middle, and you roughly end up with, well, whatever. I guess this is what comes from the calculation. Anyways, but then you compute this residue, and you get this function of the argument of the resolvent. This is you can try it yourself, where this is this universal answer I wrote down before. And then you can do a Laplace transform to obtain the Weil-Peterson volume with this definition that I introduced before. And of course, if you try it yourself, you'll see that the Laplace transform of this exactly matches with the Weil-Peterson volume that I showed you in the previous lecture. And when you plug it into the formula for the partition function, you get exactly this, which is the same as in JT. So if you have time as an exercise, you can verify that this matches with what I wrote down in the previous lecture. So to summarize, either JT gravity or the random matrix has a topological expansion in terms of this set Gn. In gravity is the number of handles or wormholes, and in matrix integral is the topological expansion. In JT gravity is computed in terms of this gluing these Weil-Peterson volumes with trumpets, and matrix integral is computed by topological recursion, where we fix the density of states to match with JT. The result of Einer and Orant did prove that both recursions are identical. So then this leads to this JT RMT duality between pure JT gravity and random matrix, where JT gravity is holographically dual to an average over Hamiltonians. So I started one of the first lecture with a picture like this, where we have this central dogma or holographic principle that a black hole from far away is described by a quantum system. Here we found that it's not described by a quantum system, but described by an average over quantum systems. And you can take two routes. One route is to think that the effect of this wormhole is just an approximation to certain effects that all black hole quantum mechanics have, or field theories in higher dimensions do to higher dimensional ADS. But you can also ask, okay, you can also ask if I include wormholes in, so we don't know how to define quantum gravity, but if you do allow for wormholes that have these nice features, then in string theory there should be some effect that is canceling their contributions when they are bad, such as spoiling factorization, but keeps them there when they are good, such that like this random matrix universality or the calculations of the page curve that I'm not gonna discuss in these lectures. So for example, we have, and this is not really about being in 2-dimension or higher, this is a general question about string theory. I just gave you an example where the dual in string theory of 2-dimensional gravity is a single theory, like the C=1 string. Another example are black holes that are constructed with ADS2 throats from compactifying in Calabi-Yau's to 4 dimensions and then looking at the extremal limit. And these are described by, in string theory by single quantum mechanics. It's just not understood very well. Well, in this case, the quantum mechanical system is not understood very well, but it's also not understood what role ultimately these wormholes play. But okay. Yeah.
So here you talk about this ensemble average.
Yeah.
So do we have to choose in some certain class of the ensemble to match with gravity? Like for example, you can study this ensemble of the minimal model or ensemble of the integral model or various type. Then does it also give the gravity dual?
But the minimal model is in 2 dimensions, right? This is a 1-dimensional ensemble of.
Yeah,
so just giving you the Hamiltonian.
I mean, for example, like does it need like a very complicated like a chaotic some theory, Hamiltonian of the chaotic theory, or could it be like some integrable Hamiltonian of the integral model, or it doesn't matter?
Well, I think it has to be chaotic because one definition of quantum chaos is that the spectrum is complicated enough that if you look at the statistics of the eigenvalues, it looks like a random matrix. So presumably some integrable model would not behave in any limit.
Even in each one, okay, I see, okay.
Yeah. So I think you should really look at the chaotics. So
Each
yeah,
one
so
also should be
that's one of the ways to interpret this wormhole that I mentioned is let's not look at pure gravity and just look at the wormhole as another saddle that like this double cone that sometimes contributes. Then that will capture the statistics of eigenvalues of a single theory. But for it to look anything like a random matrix, it has to be chaotic enough. Yeah. And then the JT gravity is like a toy model that removes everything else except this chaotic behavior and just gives you the random matrix on the nose. Yeah. Okay. So let me go back to the spectral form factor. So I mentioned that in the double scaling limit there is a universal answer for the two boundary correlator, but actually there is an even stronger result that hints at this random matrix universality. There is this sign kernel formula that you can find in Mechta's book, for example. And for any random matrix theory, if you look at the statistics of eigenvalues E and E prime at very short, when E minus E prime is small and they are both far away from the edge, then the rho correlator is approximated by this formula, where rho naught is the disk, the leading order density of states. And this affects the spectral form factor because if you take the product of two partition functions and you average, then this will appear here in the. And several aspects of this formula are understood from gravity, but not all. Let me write down the spectral form factor of a random matrix model. First, we have this slope that I already mentioned some of this in the last lecture, but maybe it's important enough that I don't mind repeating. First, we have this slope behavior that decays forever and does not really tell you anything about the discreteness of the spectrum. And this comes from the first disconnected product of two disk density of states. And from gravity, it comes from a product of the two disconnected black holes. And it decays with time forever. Then we have this ramp that I mentioned comes from this double cone or from this two-boundary wormhole. And this comes from this, from this term of this universal answer that blows up when E is equal to E prime. And this is related to the level repulsion between the eigenvalues in a chaotic system, in a random matrix. So in gravity, this ramp comes precisely from the double cone or this wormhole that I wrote down before. This ramp kicks in at times that are exponentially large in S naught. And then you could, well, in principle, you could also ask why there are not higher genus corrections that might be relevant at similar timescales. But one can see that higher genus corrections do not blow up at equal energies like the single wormhole does. So the single wormhole is really a good approximation that is giving this ramp behavior at this timescale. But okay, then we go to the final two terms that they are doubly non-perturbative. They reproduce this plateau behavior.
Excuse me, there is a question from online audience.
Yeah.
The question is, the existence of space-time wormhole implies ensemble average.
No, it does. I will mention it in a couple of slides. So if I don't answer the question, you can ask me again in a couple of minutes. Okay, so this reproduces the plateau that I mentioned before, that the plateau is really coming from the discreteness of the spectrum. And this comes from these two terms that are highly oscillatory. And you can see that this is doubly non-perturbative in gravity. So this is a cosine of something proportional to the disk density of states. The disk density of states is itself proportional to e to the S naught. So this cosine is a highly oscillating term that goes as e to the S naught with an I here. So these doubly non-perturbative effects are totally understood from a matrix side, but they are not understood at all from gravity. And some progress that I mentioned last lecture, I think, is in this. These are the authors of the paper from last year that I mentioned. Okay. So understand. So the ramp has this double cone that is universal, and we understand, but the plateau is more mysterious. And for a system with a single Hamiltonian, with no averaging, we expect the answer to be like this blue line with wild fluctuations, not really with not really any gravity interpretation other than the slope region. But for a system that has no averaging, you can understand the gravity answers as giving approximations after you average either over time window or an energy window, but within a unique theory. So if you take a theory that is unique and you do this type of averaging over time or energy windows, then it will follow the red line. And so gravity is good enough, for example, to reproduce this segment of the red line, but the answer to the question is that there will be other corrections that give you this the original blue line that we have no understanding of. Okay. I don't remember. Yeah, I think it's just SYK with a particular value of chase. Yeah, so SYK is SYK is usually defined with averaging over J, but you can also just pick some random value of J, and that will give you a unique Hamiltonian, and you can compute it with that one. Yeah. Okay, so I want to mention some comments about non-perturbative effects in a little bit more detail. So these are general comments I wanted to make, but let's go back to JT gravity and more try to see what can we say about non-perturbative effects. So to all orders in perturbation theory, the density of states at negative energy is 0. So what should we make of it? One way to see that something should go on is that should go off is that I showed you that higher genus correction blow up higher and higher at 0 energies. So that should tell you there should be something funny going on. This could mean that there is a non-perturbative shift of the ground state energy. But really, there is nothing preventing eigenvalues to take negative values for a specific member of the ensemble. So we expect to have non-perturbative corrections that contribute to the density of states in the forbidden region. And indeed, we expect the density of states in the double scaling limit to look like this. So at negative energies, we expect there to be small non-perturbative tails in the density of states. Then in the allowed region, we expect there to be oscillations related to the discreteness of the spectrum. These oscillations are the ones that give rise to the plateau and are difficult to understand, that I mentioned before, that are doubly non-perturbative. Just to mention this, the non-perturbative corrections in the forbidden regions are easy to understand. They're given by this formula, so Y is the density of states. And the interpretation of this formula, so this is exponentially small in e to the s naught. The interpretation is that this integral that appears in the exponential is precisely the effective potential that an eigenvalue feels at that negative energy. So if you ask what is the probability that I take an eigenvalue and I place it in the forbidden region, that should be exponentially small in the effective potential. And this appears here as the fact that this is a non-perturbative correction. And this is doubly exponentially suppressed in G Newton. If you remember that S naught goes as 1 over G Newton. And this is e to the minus e to the S naught. So this is a doubly non-perturbative correction that we can is a little bit better behaved than the oscillating one that I mentioned before. But a subtlety that I'm not going to spend too much time with, but all this works nicely if this effective potential is actually positive, so that this is really suppressed. Now, it happens to be that this is not the case in JT gravity. The effective potential is positive close to the edge, but then it can become wildly oscillatory and negative. This is was pointed out in the original paper. So one needs to give a non-perturbative definition of this, even the matrix model side, by doing some steepest descent contour that would make the model non-perturbative well behaved. So I just wanted to mention it to you, but actually one can find other modifications of the model, like studying supersymmetric versions where they are totally non-perturbatively well defined from the matrix model side. And then there is the more mysterious, this doubly non-perturbative but oscillatory effect. They are not small in any sense, so if you compute them for the one boundary density of states as opposed to the two, there's this cosine of e to the s naught. Naively, these are not small in any sense because the leading order density of states is exponential in s naught, and the one wormhole contribution that I computed before is exponentially suppressed in e to the s naught. It's e to the minus s naught. So in a sense, this contribution is bigger than all the contributions with wormholes. But the idea is that when you because this is highly oscillatory. When you do any kind of averaging, we'll remove it. But of course, this becomes important when you look at the extremely late times and you want to reproduce things like the plateau. And just to mention it, if you want to see a toy model where all these things are actually solvable, which is JT is kind of difficult to do exactly. There is something called the Airy model, which is the double scale limit of the Wigner semicircle. And this is dual to something called Witten topological gravity. And here, for example, you can compute the density of states exactly in the double scaling limit as a function of exactly, I mean, for any value of S naught. You can, this is not for S naught large. This is an exact answer in the double scaling limit. And then you can expand this at large S naught, and you can see that it has all these features that I just described. And this could be an exercise if you're interested. And this should also be an approximation to JT at low temperatures, because, as was pointed out before, low temperature JT has the universal square root edge that matches with this Airy model. So this is in the papers that try to do calculations of this sort. This is usually the toy model one can use to find exact answers, and then when you want to study something in JT, then you have to work harder. So let me mention about generalizations now. So this is a very specific theory of gravity that we considered, pure JT, and it's a very specific random matrix. So we can discuss generalizations when we generalize the theory of gravity, or we generalize the random matrix, and how do they match with each other. The first, yeah.
This is perhaps a stupid question, but so on the matrix model side, there is an integral of Hamiltonians with some probability for each Hamiltonian.
Yeah.
Now in SYK model, there is an average over the couplings J.
Yeah.
For each realization of J, there will be some Hamiltonian.
Yeah.
So is the probability on the matrix model side exactly the same probability for the Hamiltonian for the SYK?
Yeah, that's perhaps one example that Seok was asking also. In SYK, you have a lot of structure because you have these fermion operators. The Hamiltonian is a sum of products of fermions. It's not a matrix, but fermions are vectors there. So you have a lot of structure from the Hamiltonian point of view that are more than just a random matrix. But you can understand SYK as an integral of this sort. But what will happen is that here I assume that the probability distribution is given by this simple matrix potential. And if you try to, yeah, you can do as an exercise to, or one can do to derive this P of H for SYK, and it will probably look like something super complicated with, it will not be written as a simple, in terms of a simple matrix potential, because the average is done over Hamiltonians with much more structure than just random matrices. Okay. But to see that from gravity, you have to have more matter, you have to have more structure in gravity to see more structure from the boundary. Yeah.
And I have a related question.
Yeah.
So SYK is the averaging of this correlation function or free energy. I mean, it's quenched average.
Yeah.
But this average of the partition function is annealed average. In large N, it would be same. In leading in N, but the subleading it's not clear, and maybe it's
no. Well, here I'm. This would be the simple average, the average that is easy to do. In that sense, this is the gravity is equal to this average. I think what you are saying is that if I want to compute the average of the free energy as opposed to the average of the partition function, then I have to work harder because I have to put replicas and take some kind of limit. I think that's as difficult in gravity as it is on the quantum mechanics side, and so you can make a similar question on both sides, and they both would be equally difficult.
Okay.
Yeah, there was some papers trying to study this. I don't remember the authors. Yeah.
JT plus specific matter content.
Yeah, yeah.
And that matter content is perhaps known or what?
It's not known very well. I mean, well, no, it's known because you know the spectrum of SYK, but.
Yeah.
I don't know of any useful description of, like for example, if you instead of talking about SYK, you talk about the quantum the mechanics that appear from string theory, compactified Calabi-Yau, that give rise to this black hole, then that would be. Then I would know what the dual is if I understood that better, because it's this string background.
Okay.
But in SYK, we don't have any useful description of what the bulk is.
Okay.
Yeah.
Okay. Thank you.
Other than JT coupled to stuff at low temperatures. Yeah. Yeah. Okay. So the easiest generalization one can do, well, not the easiest, but the most straightforward perhaps, is to consider unorientable surfaces, which also has a history in non-critical string theory. So I've been summing over oriented surfaces, but you can include crosscaps and things like that. And that can be shown to be dual to, so far I've been using the GUE ensemble, integrating over Hermitian matrices, but this generalizes the GUE to the GOE or GSE, where you integrate over orthogonal matrices or symplectic matrices. And there the interpretation is that from the boundary theory is that if you include an orientable surface, then the question is whether you have time reversal symmetry or not, and is this Hamiltonian arbitrary Hermitian matrix, or does it have more structure? And this is how this generalization in gravity translates to other matrix potentials. There are actually 10 classes of matrix model ensembles. I will not go over all of them. I just mentioned one, the complex matrix ensemble. And this is actually dual to n equals 1 JT. This is a supersymmetric theory of JT that is not the one I mentioned in the beginning. The one I mentioned in the beginning has n equals 2 or 4. N equals 1 is too low to have anything interesting. It doesn't have an R symmetry, for example. And in a sense, you can just see it as a more complicated version of bosonic JT. But anyways, the density of states is this. If you try to compute the Schwarzschild density of states, you get this Koch instead of a Sinch. And at large energies, it matches the classical answer, but at low energies, it blows up as 1 over square root T. This is 1 over square root T. And this would go against the random matrix universality, where you expect the square root H to be the universal low energy behavior. And the answer is that this is not a Hermitian matrix ensemble, it's a complex ensemble, where the random matrix is not the Hamiltonian, but is the supercharge. So the Hamiltonian is Q squared. If your theory has a -1 to the F, then the Q supercharge can be written in this way. And the random variable is not H, but this matrix M. And then when you study this random matrix ensemble, you'll find that is dual to n equals 1 JT gravity. And this happens when you sum over spin structures in a specific way. You can sum over spin structures in different ways, and then there are different ensembles. And finally, I don't know how much time I have. Okay. It's until 12:20, right?
15 minutes.
Okay. 20 or 15, okay. Okay. So let's go back to the JT gravity on orientable surfaces and the integral over Hermitian matrices. And I think this I already mentioned as an answer to a question in a previous lecture. Each side of the duality is determined by one function. On the left, you'll have, in principle, if you try to generalize it, you'll have pure gravity, and that's described by a dilaton potential. And on the right, you have a matrix integral that is described by a matrix potential, which determines the disk density of states. So a question one can ask is, are there deformations of JT gravity or theories with more general dilaton potentials whose dual are ensembles with different values of the matrix potential or the leading order density of states? And the answer is yes, that I wanted to describe. So this has been studied for the past couple of years. So these deformations of JT gravity are can be described in two ways. One way of describing them is that I do this topological expansion with the wormholes and do the path integral, but now I allow the presence of a gas of defects, which I introduced by hand. So I allow conical singularities in the geometry. I integrate over all the positions where they can be. I integrate over any number of these conical singularities, and each is characterized by a weighting, like a fugacity, meaning like if I include 1, I put a factor of lambda. If I include 2, lambda squared, etc., and the deficit angle. And including this gas of defects can be shown to be equivalent to shifting the dilaton potential by exponentials in the dilaton. So this is the JT action, and then I add something proportional to lambda times the integral of e to the -5. And the way to show it is that it's easy to see that inserting a defect and integrating over the position is equivalent to inserting this operator in the JT path integral. And the reason is that this is exponential in the dilaton. If you remember, the JT action is proportional to the dilaton. So if I integrate out over the dilaton, then that imposes that r plus 2 is not 0, but it's equal to the delta function localized at the defect. And the final step is to sum over the locations. Well, the sum over the location is this integral, but to sum over the number of defects. And when I sum over the number of defects, that just exponentiates this insertion to, and it will look like a shift of the dilaton potential. And that's what this is. I sum over the number of defects with this fugacity, and then this exponentiates, and now this appears as a shift in the action. And theories of pure gravity with dilaton potentials of this form can be solved in this defect expansion way and can be shown to be dual to a matrix integral as well. And in order to do this, we need to, the procedure we will use is, again, to cut and glue in geodesics and glue with trumpets, but now we have bulk surfaces with geodesic boundaries with conical singularities. And there is a similar Weil-Peterson volumes for hyperbolic surfaces with handles, boundaries, and cone points that one can use to solve this theory. And the only restriction is that the deficit angle is big enough, or this parameter alpha is smaller than 1/2. Alpha is this. Let me show you. Sorry for going back. The deficit angle is 2 pi times 1 minus alpha. So if alpha is equal to 0, this is a cusp. If alpha is equal to 1, this is a marked point. It's just nothing, no defect. And if alpha is small enough, then I can only do this procedure if alpha is small enough. So for example, I have corrections like this where I can find the geodesic. If alpha is too big, or meaning that the defect is too blunt, then there might be situations where there is no geodesic. So in a picture like this, there might be no geodesic connecting this bulk surface to the boundary, and then I cannot really cut and glue. So we have to restrict to sharp defects where alpha is more than 1/2. But these Weil-Peterson volumes in that regime is known. They are just an analytic continuation of, so you replace the defect by a boundary, and then you pick an imaginary boundary length. That's just a result that one can show. It doesn't matter where it comes from. Perhaps I just want to tell you that I know what the answer is, so then you can use it to solve the theory. And the way to solve the theory is that now we have to sum over adding wormholes or adding handles, but then for each number of handles, we also have to add this defect expansion. Okay, maybe let me skip this and just say that to show what the dual matrix is, before we show that the duality works to all orders in the genus expansion, I need to tell you what the leading order disk density of states is. That was an input, if you remember, in the matrix integral that determines everything else, and then that's matched to gravity. So there is one calculation that I should be able to do explicitly, which is the sum over defects, but with no handles. So this will be the analog of the disk density of states, but for this deformed theory. Is there any question about that? Since I skipped a couple of slides. Okay. But something nice about this is that this sum over defects with no handles can actually be done exactly. Or well, not exactly, but it can be written as a simple integral of Bessel functions that is... I cannot do the integral, but it has some nice features that make this actually useful. So this is an integral. Everything is proportional to e to the s naught, since this is the leading order density of states. It depends on the fugacity of the defects, lambda and alpha, which in turn determine the dilaton potential. And it depends on a parameter e naught, which is a shift of the ground state energy. So in JT gravity, the energy spectrum starts at 0, but when you add these deformations, that can move around the location of the ground state energy. And this E0 is a solution of this implicit equation. There is this combination of Bessel functions. And okay, this is what one can find by using the Bell-Peterson volumes for these surfaces. And then you can compute it. So here I'm just showing you some examples. So if for some specific values of alpha and lambda, so here you see that the curve looks a little different, and it has the dashed line is JT and the black line is deformation. This is for lambda negative. This is for lambda positive. And one interesting feature is that if the deformation is too big in a certain for a certain sign, then there can be negativities in the spectrum, which indicate that the model is even perturbatively is even ill-defined. Doesn't have even a perturbative definition. Perturbative, I mean, to leading order, even in the disk approximation, this theory would be sick. And the interpretation and fate of the models for these particular dilaton potentials that have this density of states is an open question. I don't really know what to do with it. But we wrote a paper with Felipe Rosso where we study a similar issue in deformations of n equals 1 JT. And then what happens is that there is an analog of the Gross-Witten-Badia phase transition where this saddle for the matrix integral, so this was done from the matrix integral side. This saddle that gives you this one cut non-unitary density of states actually is not the leading one. There is a one that dominates more, which is one with two cuts, where the analog of, well, we did it for n equals 1, but the analog for bosonic JT would be that this negative part gets removed and now we have two cuts. So it's the analog of what happens for unitary matrix integrals in Gross-Witten-Badia model. But this is done from the matrix integral side, but from gravity, it would be nice to have a gravitational interpretation of these phase transitions where you pick some theory of gravity, it looks perfectly fine, then you compute the density of states of the dual, is totally bad, and somehow something magically solves the problem, but we don't understand from gravity how that happens.
I have a question. So can, like a similar to this picture, you can study like a two semicircle and when they close each other.
Yeah, that's another theory of n equals 1 JT.
Yeah.
Yeah, in n equals 1 is for certain theories it's literally the same as the gross. It's not the one I described. The one I described is the complex matrix, but and that's for a particular way of summing over spin structures. But if you sum over spin structures in a different way, then the random matrix is the universality of the two cuts merging in the.
Yeah. Then each cut can be understood as like each gravity, like a.
No, because this is understood. The theory is dual to. The gravity dual is understood after the two cuts merged. It's when they are about to separate, but didn't separate yet. Yeah, so that's when, and the logic is, well, should I say it? Yeah, this I can explain this. Yeah, let me go back. Here, yeah. So here, and this depends on how you sum over spin structure. Here, I assume that I have a -1 to the f that is not broken, so I can write Q in this way. If I sum over spin structures in a different way, and I can tell you how if anyone is interested, then you can consider theories of gravity where the -1 to the f is anomalous. And then you don't have any right to write Q this way. Then Q itself is a random Hermitian matrix. And then what you should write is the disk density of states, not of the energy, but of the eigenvalues of Q itself. And then if you try to translate this cosh of square roots to a density of states for Q, then it looks like something like this. Large energies, it goes to exponential, and then it goes to some non-zero value, and then back. And this is precisely the two cuts of the unitary, for example, matrix model that after they join, looking very close to the location where they join. Yeah. Okay. But yeah, for example, in that case, the negativity appears is exactly the phase that solves the negativity is the phase where the two cuts separate. But I don't understand from gravity what that phase is. Okay, so Yeah, so this is the disk density of states, but we can also work out this cylinder or double trumpet or this two boundary wormhole. And I mentioned that this answer is universal for a double scale matrix integral, and it has to be given by this formula. And in gravity, you have to sum over geometries like this that have two boundaries and have any number of. I'm not allowed to add handles because that would be subleading in the genus expansion, but I should add defects and should resum over defects. And one can show exactly that after you resum over defects, the answer is precisely this universal answer with the shift of E naught that is equal to the shift that appeared in the disk. So everything is consistent. So I can draw the same diagram that I drew before. So in these deformations of JT gravity, we can write the topological expansion. For each term in the topological expansion, we can compute it in gravity by fixing the number of wormholes, but summing over all defects. And on the matrix integral, we can pick the disk density of states and then use the same topological recursion that I wrote before, but for this new density of states. And then there is another theorem by the same guys, Einar and Orantin, that shows that these two prescriptions match to all orders in the genus expansion. I don't remember I think they don't call it deformation theorem, but basically they show that if there is a solution of the topological recursion, such as undeformed JT, they show how to construct new solutions of the topological recursion. And what you can show is that this new solution is precisely adding this gas of defects. Yeah, so this gives a nice generalization of the previous JT random matrix duality. So maybe one can call it pure dilaton gravity random matrix dualities. Now let me mention just two more generalizations. I think that's the last thing I was going to say.
Quick question. So if you add these defects, possibly different flavors of defects, I don't know, with different angles. So you sum this contribution to the deformation of the dilaton potential. Can you construct generic functions? Is like some Fourier expansion, or are there still special functions?
So this is the formula. So I cannot construct. I mean, if I allow lambda and alpha to have any value, then this is just a Laplace transform of the. Then I can even make this sum a continuous integral, and then I can rewrite, instead of the dilaton potential u of phi, then I can rewrite lambda of alpha, which would be like the Laplace transform of u of phi. So in principle, one can do that. The only problem with that, and the reason why I don't really know how to solve this for any dilaton potential, is because of that restrictions of alpha being smaller than 1/2.
But then you had a slide that said that you can solve the problem. But
what?
In one of the slides, it was written that you have another way to do the computation, even if alpha is.
Oh.
I don't know. I read it quickly.
I mean, here maybe what I meant is that the surprising thing is that one can even for these sharp defects, one can resum this first line.
No, there was a slide, I don't remember which one, that was saying that when alpha between 1 alpha and 1, you can use another method. Don't remember which slide.
Sorry.
We will use a different method
I removed
later.
that because I didn't think I would have time anyways.
Okay.
So we will not see it. But
but there is a method.
There is a method, but I just don't understand it very well enough. So I mentioned before that there is a connection between JT and the minima string. And I don't know how to solve the problem within the JT language for when the defect is in this range. But when you map the other problem that you can solve to the minima string, and then you see that a limit of the minimum, you can deform the minima string, and the same limit that will give you JT without the deformation now gives you the JT with the gas of defects. I can tell you what that is. But so here this is just a check. But the solution of the minima string actually doesn't care about this bound. You can extend the solution to any value of alpha, and then you can take the JT limit, and then that predicts what the answer is in this range. But I don't have an independent calculation. So we wrote the paper where we just make the observation that we can propose a solution from the minima string, and we can make some checks. For example, if alpha goes to 1, you should reproduce JT, because then you have just a gas of mark points, which is nothing, essentially. Should give you back the undeformed theory. We make some other checks, but That's what I meant.
And there is no phase transition at 1/2. I mean,
Yeah, there is. So if you take the answer
there is.
here and you analytically continue, you just analytically continue in alpha, you will get the wrong answer.
Oh.
Yeah. And there is a Gauss-Bonnet argument of how many defects can you merge such that there is a geodesic surrounding them, which is a more general version of this. So when alpha is 1/2, you almost, as alpha goes from 1/2 to 1, your more and more defects are allowed to merge, and this is discontinuous. It happens in steps of that are determined by Gauss-Bonnet theorem. So it's a very non-analytic function of alpha. Yeah, so that was the first expectation when in 2020, or the first time we wrote this, that, okay, you can just analytically continue. But then when you analytically continue, the sharp answer to alpha equals 1, you get answers that it doesn't make sense. You get answers that are that don't really make sense. So then it's okay. From the minimal string, you get that, oh, actually, you're not really allowed to do that. You need to do a different calculation for alpha. Yeah.
Thanks.
Sure. Yeah, and I think understanding this limit of alpha close to 1 is not just technicality. The interesting thing of sending alpha to be close to 1 is that I constructed the dilaton gravity as a deformation of JT by adding defects. But then you can also ask, how do I see from the defect that the defect somehow condensed to change the metric? Because if the dilaton potential is not linear anymore, then the solution should not be pure ADS anymore. So how can I see that I have a non-ADS dual from resumming the defect? And in order to see something like that, you need alpha to be close to 1, because when alpha is sharp, one way to see it is that, let me see, where do I have it? When alpha is too small, then this decays very, very rapidly at large dilaton. And what this means is that this deformation doesn't affect the large energy part of the spectrum, only affects what's going on near the edge. But that is the quantum regime, where you don't even have a classical description to begin with. So you want the dilaton potential that affects the large energy part so that you can interpret as non-ADS geometry if you want to see some features that are not ADS. And in order to do that, you need alpha to be small, so that, alpha minus 1 to be small, so that the dilaton decays slow with a large, so that the potential decays slower at large dilatons. Yeah. Is there any other question? Yeah, so, okay, this I think is the last that I'm going to say. So their generalization is, so far we did pure dilaton gravity, but we can also do pure dilaton gravity coupled to gauge fields. This is also exactly solvable. And here, just to tell you the upshot is that the matrix ensemble is a direct sum over statistically independent Hamiltonians in each sector labeled by a representation of the gauge group. And the idea is the following. This H is supposed to be the Hilbert space. Because you have a gauge field in the bug, the Hilbert space has a global symmetry. So because you have a gauge field in the bug, the dual quantum mechanics has a global symmetry. So you should be able to separate the Hilbert space into sectors that transform in different ways in different representations of that global symmetry. And because it is a global symmetry, the Hamiltonian should be statistically, you should be able to write the Hamiltonian within each Hilbert space of a fixed representation. So the Hamiltonian should take this like block diagonal form. And then this is the structure given by just the fact that you have a gauge field and a global symmetry in the boundary. And then the generalization of the matrix ensemble is an ensemble where each block corresponding to each representation in the Hamiltonian is statistically independent. So you have a collection of random matrices where the matrix is the Hamiltonian in each of fixed charge sector, fixed representation. And again, this was proven to all orders in the genus expansion. And finally, a more mysterious duality that is not understood very well, that I think is perhaps the most interesting one to work out, is the dual of JT with propagating matter. So in 2 dimensions, gauge fields are not propagating modes, but so we can ask what happens if we have dilaton gravity coupled to matter. And there was a proposal recently by Jeffries and collaborators that if you just add a simple scalar field coupled to the metric but not to the dilaton like we did before that was an approximation, but now I take it as a toy model, just that's the full action. Then they proposed that the random matrix dual is a 2-matrix model where realized is ETH because the matrix elements of the operator that is dual to that matter is random itself, so this is like in ETH. But as of, differently from ETH, also the energy eigenstates are, or the Hamiltonian is also random. And this is difficult for 2 reasons. The first reason is that when you try to compute the path integral of JT with matter in surfaces with wormholes, the answer actually diverges. And one has to regulate it somehow, and I think that regulation is not very well understood. And secondly, this 2-matrix model is not solvable. There are some matrix models that are solvable with 2 matrices, like the Ising model on a random lattice. That's a 2-matrix model that can be solved. But the potential in these models are such that is not solvable. So they do some checks, but they cannot really prove it in any way. So I think there is some more to be done in this direction, because perhaps this is the theory that would look the closest to something like what arises from higher dimensions. Finally, well, I had these comments, but we already discussed this last lecture. There is this connection to... So this gave a very nice new interpretation of the matrix, or this dual role, where in the old days the matrix was used to triangulate spacetime, and the interpretation in the old days of the double scaling limit is that it's the limit where the triangulation becomes continuous, so the surface becomes continuous surface. But now we gave a new concept where this matrix is really the dual Hamiltonian, and this is perhaps closer to the original ideas of Wigner of how to apply random matrix series to chaotic systems, and in this case we're applying that to black holes. Finally, there are other applications that I didn't have time to discuss, and they would deserve a whole set of lectures about how wormholes in certain cases can resolve the information paradox when the black hole is allowed to evaporate. So the entropy of the Hawking radiation naively grows forever, but if the black hole is described by a system with finite entropy, then at some point it has to go down because the total system is pure. Then to purify the Hawking radiation, you need the black hole to have at least as many degrees of freedom. And wormholes of this kind, when one computes the entanglement entropy with a replica trick, are the ones that are responsible for the page curve. And as a last comment now, there are other applications of JT gravity in the Sitter space. In the spirit of lectures 1 and 2, when you couple it to matter, it describes the Nariai limit of black holes that appeared in Qumran's lecture. So when black hole is very close to the black hole horizon becomes very close to the cosmological horizons in the Sitter, there is a DS2 throat that appears. Well, it's not a throat, but there is a DS2 region. And one can study, again, in the spirit of the second 2 lectures, pure DS JT gravity. And there is a random matrix duality, but it's very unclear what the... there is a random matrix that computes it, but it's unclear what the interpretation is. It's not the Hamiltonian because the boundary is not time-like, but it would be nice to know what the right way to interpret it is. So okay, it's just some general comments. So we studied the role of emergent broken conformal symmetry and near extremal black holes. Showed you in the first lectures how the Schwarzschild model controls the spectrum and dynamics of these black holes and the connection between the horizon, maximal chaos, and thermalization. We studied in the second lectures how gravity has access to information on random matrix statistics of black hole microstates, and it's important to include wormholes to see this. Something that was underlying everything that I did was that the quantum mechanical properties of black holes is captured by the gravity path integral. This is not obvious. We don't know how to quantize gravity, so when we do the gravitational path integral, it's an assumption that this is the right thing to do. And perhaps mostly from quantum information come the most non-trivial tests that the gravity path integral really has fine-grained or really captured the quantum mechanical properties of such black holes. Finally, we study these wormholes that are good approximations to some features, but they spoil factorization. And what the ultimate role of disorder in fundamental theory of gravity is an open question. We think that there should not be any disorder, at least that's what comes from examples, but would be nice to understand better. Okay, thank you very much for your attention.
Thank you very much for the very nice talk. Please ask questions.
So going back to the double matrix model that you mentioned before not being solvable, you mean not even in some kind of Large-N limit where density of eigenvalues double in two variables or something like that? Or you mean not solvable in an exact sense? I didn't understand what you meant by not solvable.
Yeah, I guess I meant in an exact sense. Like in the other matrix model, in the one matrix model, I know how to do it order by order in the genus expansion. But in this model, I don't know. Maybe I can compute to leading order, and that's what they do in that paper. But there is no way to solve it.
Okay.
I don't want to find the exact answer. At least some technique that would at least allow you, if you want, to compute added orders. And well, I guess you could say that you can integrate the matrices, but something useful. I don't know of a useful way to solve the model.
Thanks.
Other questions?
There is a question from online audience. So he's basically considering the Short-N quantum mechanics for the disk amplitude, and this is basically controlled by Liouville potential. So the question is, what is interpretation of the potential in terms of random matrix theory, or some other intuitive interpretation, especially about the Liouville wall side?
What do you mean by the Schwarzschild being controlled by the Liouville potential? I don't understand that part of the question. I mean, I don't know. Maybe I can repeat what I said last time. So double scale matrix integrals, one matrix integrals are dual to the 2, p minima string. And when you take large P, the Liouville mode becomes weakly coupled and becomes classical. And classical Liouville means that surfaces are hyperbolic with constant curvature. So somehow that would tell you that if anything is summing over hyperbolic surfaces, that should be the large P limit of the 2, p minima string. And if you take the spectral curve of the 2, p minima string and you take the large P limit, then you get the Schwarzschild quantum density of states. So in that sense, they are connected. But I don't know if that's what you're asking.
So I think he asked like Schwarzschild, from the Schwarzschild theory, you rewrite down the field redefinition of this F to become this Liouville, this.
No, that's a different Liouville.
Yeah, so that Liouville.
Okay.
So that Liouville potential, what is the?
Yes, so there are two ways in which Liouville helps. So, in the way of lecture 2, what we did is that we need to do the path integral over the Schwarzschild mode, and then one way to do it is that you can show that two-dimensional Liouville viewed as a CFT, not as gravity, but as a CFT that has a limit where it computes the Schwarzschild path integrals. That doesn't know anything about the random matrix. It's just a statement about the Schwarzschild path integral being a limit of the Liouville path integral. Then the Liouville that I was mentioning in this lecture was Liouville gravity, which is what remains in the conformal gauge of coupling a CFT to worksheet gravity. And in that case, that knows about all the higher non-perturbative corrections, and there is that Liouville is not really describing the Schwarzschild. I mean, indirectly it is, but it's describing the actual gravity in the bulk. So the same theory can appear in different ways, I guess, and I don't think that it's related in any way. Because as I said, for example, the Schwarzschild doesn't know anything about higher topologies.
Any other question? If not, let's thank speaker again for the nice 4 lectures.
Thank you.
All right, so tomorrow is the last day of the school, and this afternoon, a lot of you guys put really nice posters, but I guess this afternoon probably all poster has to be removed. Thank you.
Generic Dilaton potential, right? Not generic, but is there like other local minimum? So I think like other local minimum, so that is like a usual minimum in ADS, but
yeah, that's what I meant. So yes, you can have other solutions that are not ADS, but so yeah, that's what I mean. I think it would be nice because one way to solve the theory would be you take the new Dilaton potential, you find a new geometry, and you try to compute something, or you have to resum over the defects, and the two should match in the classical limit, and that's not easy to see.
So what you obtain this like this deficit, and this one is just locally ADS.
Locally ADS except for the compounds.
Yeah, exactly.
But somehow those defects should, like, I don't know, condense or something like that to, after you sum over a lot of them, they should describe the actual change in the metric. But that's hard to see because the defects are easy to solve in the limit where they are, quantum mechanical effects are large. So that's the, so then what you need to solve is to solve it for alpha close to 1, and then that's difficult, but okay, that's just the way it is. Thank you. Yeah.
About 2D CFT thing that I went to.
Yeah.
Is there any research about higher dimensional CFT?
Sorry, let me 1 second. Yeah, sorry.
Is there any other research for higher dimensional CFT?
Yeah, I just don't know how to do it because I think it's
say someone drops in a medical store and those temperature has an emerging conformal symmetry. Conformal I mean SL2R, not extra. Like I'm looking at some state that breaks the UV conformal symmetry. I'm putting it in a sphere and turning on some charge. So I lost the symmetries by my choice of state. But at very low temperatures, there should be again an emerging conformal symmetry, but in normal temperature. If someone tells you that that statement is true for some reason, then it has to be described by the Schwarz matrix. You can argue with my effective theory arguments that laterally goes to most of the broken conformal symmetry, even without talking about JP. So the statement is, the question is, okay, we have an ADS tool, so according to everything we know about ADS-CFT, that should carry that there is an emerging conformal symmetry normally. Whether you show that it's there or not, I figure that way it's easy to assume. But if everything works in the standard way we expect from ADS-CFT, then you should have the symmetry working in the area. Because we expect the area to be interior. The more you go into the interior, the less you describe the linear physics of the but related to Cameron's lectures, and perhaps one would expect that ADS2 would be a stable element. So maybe what you should show is that actually that cannot happen. And the interpretation would be that if you cannot have a Schwarz, then that means that you cannot have an ADS2 strong immersion that is stable all the way down to zero. Unless you have supersonic. Okay.
both sides we have different FTC.
Yeah, and so
Primordial.
So you get the well, if it's a mathematical name of the line, you get Flushing is the biology category. Now there is a alpha induction. And alpha plus minus. There are two distinct. Now here I'm assuming that both sides are unequal. Right? Then so that's it's just is you can put Wilson line here or there, and that's just so let's say this guy is alpha plus I and so okay. And so there's a theorem that here the simple well, for any simple and there is alpha plus and sine. It's the pair of yes plus or minus.
Plus minus just means the side, right?
Yeah. Alpha s wi. This is not necessarily simple, but this includes as a simple content.
So simple means primary or what do you mean?
Oh, simple means that there's these categories and object, but there are also something like these sum over arbitrary sum with positive non-negative integer coefficient.
Okay, they are not simple.
So this is non-simple.
If category is more than 10 category, they are just with the primary.
Yeah, so these are the Wilson lines. Wilson lines with a small representation. So if you put very large representation compared to its level, you know that's so those are and so in biology category, so even though this is a simple, even if you pick simple thing, this wi there is a image. This is not necessarily a simple.
In terms of primordial.
Yeah. So it can be like some different parameters. So yeah, but the statement is that any simple is inside some image of alpha inversion.
I see.
And that can be understood in this figure. So as a lemma, the A simple means that no non-trivial self-intersection. No non-trivial operator on A.
I see. All the line operator should act on it trivially.
Yeah. So all A. Sorry. operator
on
on A, and so this should be this is just multiple the number times
Okay.
trivial. Okay, so that's equals to simple dimension.
Okay.
So but here even though if this is this alpha plus, but then there might be something like this configuration.
So this is the topological line.
So this is different topological line.
And then the surface and the line is set.
Yeah, and this can end on the surface.
I see.
Oh. The statement is not this.
The other way.
Statement is WJ and statement is
I see.
I have to put the other side. So well, but okay. So the simple case is this. So then so then this after reducing the interval, this looks like just a point after reducing. So this gives you non-trivial operator on the image of the reduction. So that renders this image to be non-simple. So the simple line can be.
We shouldn't have such object here.
So to do that, you so there is a non-trivial operator, but you can cook up cook up a projection by summing this operator and trivial operator. So you can get the projection operator. So then so that's the I'm assuming unitarity. But if it's unitary, then I can always cook up
projection.
The projection operator out of this non-trivial operator and the identity and some results. So then the simple factor is given by just a projection. I mean smearing this projection operator. So this is going to P projection means P squared equals to P. So putting many is equals to putting one. But anyway you can smear it around the line.
Is it already possible for any WI?
Yes, it can be for unitary this can be so this is the most generally this line looks like
That's so simple.
Yeah, simple. So this kind of thing is in my paper with about the 2D adjoint 2D Sohan and so far.
Okay. Okay. I read it. Joel and you.
That's it.
Okay. Good.
Yeah. So symmetry in adjoint 2D adjoint 2D.
Very good.
So yeah, we use this kind of technology.
You seem to understand line diagonal ones. This picture is crucial. So I'm thinking of how to realize this kind of surface operator together with this construction of like a plus minus in terms of.
So we do the example coming the non-diagonal safety coming from the embedding of the field 3 into 801. This is conformally means the central charge. Our central charge for this and this is the same. This equals to H.
I see.
And so, in other words, this adjoint fermion in adjoint of this thing. And this is the vector of this fermion. And the level.
I see.
So then in this case, there's a we study a non-diagonal. So we study the fermion event modulo the minus one to zero. To the bottom. This theory is a non-diagonal safety under this case. Well, both this, but also this.
But for this one, we have MTC, right?
So for this, so this guy is diagonal safety under SO3, this SO8.
Yeah.
But then we are disembedding. So this conformal embedding means that there is a topological interface between this and that. And as here, this theory is non-diagonal RCFT. So yeah, and we wanted to study this SU3 adjoint QCD. So we need to study this non-diagonal. So that's the example. And we analyze how the alpha induction, how is the alpha image of alpha induction can split into this fusion rule.
So is it just there may be net competition to this one, right? It depends on the computation.
Oh yeah. So here to here there's a condensation.
Oh, I see.
Here to here, this thing you can well the other direction. So here to here it's this is first this is PwC and a condensed particular algebra. So that okay. So this S itself is algebra, the condensation algebra. The topological surface which are sanitary, which is 2D so-called one gauge of condensation. So gauging but on codimension.
Oh, I see. So you took some subsystem and you gauged the symmetry only along the subsystem.
Yeah. Well, yeah. This algebra is not non-invertible, so it's not really the usual symmetry, but something unlike. But this algebra is zero gaugeable. Instead of putting S, you can condense on the codimension zero space.
Okay.
And do the half gauging, and then you get the topological interface between these.
I see.
So actually in this case we can secant this S and then here the SU3 in this case SO8.
Okay.
The one SO2.
I see.
And
so this is really condensation defect. We glue them together.
Yes.
I see.
Yeah, in this particular case. Yeah, that's the case we are now.
So it's the realization of non-diagonal.
It's a level 3.
Yeah. In one of my papers, I studied this kind of SCC level, the H fermion charged under adjoint representation of SCC level 3. And that is non-diagonal RCFT of SCC level 3.
Okay.
topological operator inside.
Here on this paper with the Johar in 2020, maybe. Yes, I agree. Very good. Looks like all this categorical business is from mathematics, interpretation of this method to physics. Wow, very complicated.
And this is why, I mean, well, actually, I don't know you call the Fuchs and Schweiger mathematician. So this business is started by the Fuchs, Rankel, and Schweiger.
No,
There's a
Fuchs, I know that guy.
Oh, I see.
Fuchs was, I met him recently also. And 93 when I was sabbatical and so on, he was my office mate. Except he doesn't say anything. He just typing in it. He was like Costa or something, principal from Germany. And then he wrote the 2 books on Cosmology and consulting. A very hard-working guy in Sweden. And then I didn't know about any of this work until I was studying freedom categories or the tensor categories. But 3 years or 4 years ago, I met him and I said, hello, long time no see. And when I saw him 30 years, he was a young man, but now he's an old man. For other 2 guys, I don't know. But he wrote a paper, 2 papers with this famous Swiss physicist, mathematical physicist. And so I would say they're physicists. I don't think they do many theorems. I mean, mathematical physicists, they love most of the papers, books they write, I can understand. There's no theorems, very easy to understand productivity theory. And I was really, but then there's another group of people in Netherlands. I think he's in the 80s now. He was before this postgrad, he was talking with Fresco, Darnaville and Isenines and all that sort of things. Then clearly he was one of the first guys talked about Fermion condensation. Heinrich is trying to saw them semi-condensed But so before Fuchs and those guys, there was a paper by French guys. I was reading some of it. And they had defect lines, Jugo and then some Onu or some mathematical physics or something.
Yeah, so Okinanu is
Okinanu. He's one of the prime mover in this game. Very early game. I mean, nobody.
Yeah,
don't
so
know
there's Okinanu rigidity theorem that basically says the diffusion category, the solution to the axiom of diffusion category are isolated. So there's no for the 1 plus 1D system, the set of symmetry, possible symmetry is discrete. There's no continuous family of possibilities.
I see.
So other thing.
True.
Yeah, so I remember opening one of his papers on this. But other thing you mentioned about topological potential and Dirac algorithm and resonant pieces. So there are some things which I completely follow. You study this about a E8, I mean, no, monster. As a rational, kind of a rational component, there's only one primary, which is vector. But as a Dirac-related or as a subset, there are like 190 conjugate classes, so there are 190 defect operators maybe. And then there is a Childen rule. I don't think the people worked out Childen rules of 190 defect lines or something. Which is
So they don't correspond to Berliner lines in this.
No, there's only one primary.
There's only one primary for the
monster line.
Of course, the whole classification of topological line monsters safety.
There's some right, some list of icing and some pairing has been done. Right?
Yeah.
But as I said, there are a lot more. There are more structures, and which is has been explored. Even this Japanese mathematician, this is not Keiki, but Pierre Keiki, there's something about the inherent monster, and then this famous well-known that suppose I have two elements in two-way conjugate classes. If they are not identical, then I multiply them together, then I can use 3A, 4A, or 1A, but you will extend the EA to design. And then there's corresponding chiral algebra here. You have energy momentum tensors together, then there's a similar structure appearance. And this some this is very famous word, mathematician. This name all the time when I was writing a paper by computer. And so it looks like even 2A, there's a, if two elements there are 3A, then obviously there's not single boundary operator, there's something more in there. And even getting that kind of structure will be very, very nice. So giving some constant meaning from this. So, this is required now.
No question, just here.
Okay.
Your discussion.
We have 8 minutes. Maybe you need to have some time to 저녁 민성이랑 같이 먹으러 가죠. 좋습니다.
I'm going for
パーションファンクションの話しかしなくて、そうですね、多分なんか違って、なんかまあ、オペレーターがで、それにメッシュを組み合わせると、まあ、はい、まあ、なんかここら辺がちょっと、理由が書いてあるのは、まあ、こういうコンフィギュレーションを例えば考えると、で、何の点かっていうと、A って、和だったので、それは、G アクションでアップしたやつでは言われるんだけど、これって、実践これが G シングレットだと、和を平均を取ってるので、平均を取ってるので、これ2の G シングレットは、大事なのそうだけど、だけど、これを名前を変えればいいだけなので、平均を取ってるのはシングレットですけど、これ、なるほど。なので、こういうことやると、オペレーターはシングレットにプロジェクトアップする。もともと存在しているオペレーターをシングレットにプロジェクトアップする。というのは、これをゲージ化と呼んでいるモチベーションですね。ていうか、自分の中のゲージ化のインデックスに局所的にこのゲージが成り立つ。 それが分かってない。それは、はい。どうしよう。いや、ディスクリートゲージフィールドみたいなのを定義することができるんですけど、それは、それを避けたんですけど、まあ、メッシュで言うと、一個入れるっていうのは、結局これ、はい。こう、これ辺にこう、ああ、はい。リルペーメントがあって、それで、ジャンクションのところで、コンシステントっていうのを、はい。はい。これはどう思うかというと、この見方はこれを、このメッシュの区切られているところをこのタッチだと思って、ここをそのトランジションファンクション、デュアルパロコニック時のトランジションファンクションがこれで決まっていると思うんですけど、はい、それからフィールドがここからここにフィールドとここにフィールドが、それでひねられてロースされているというこれメッシュがある。で、それ今回多様体をこうそれぞれなんか一個一個のちっちゃいパッチに分けてて、それぞれにゲージバーが住んでるみたいに見える。そうするとそのパッチの上ではゲージバーがこれいわゆるフラットゲージバーって感じなんで、ディスクリートだからそのパッチの上ではゲージバーがなんですけど、縫い合わせるときにゲージ変換したくなるのが、そういうので1個バックグラウンドにあって、それについて輪を取るので、それをゲージバーをダイナミカルにしていく。ああ、なるほど。あ、わかりました。はい。で、そういうのが、ありがとうございます。時間が、大丈夫ですか？まだ大丈夫かな。はい。どういう、具体的にどういういや、あるのはいいんですけど、いや、これはかなり、だから、それではないですけど、だから、RCFT であっても、いいですよね。言っていた方は、RCFT で、これなんかハイララジルが C 上の、で、これがそのビラソルより大きいとか、そうすると、これのペアイングラインって言うんですけど、これはC をプリザーブする。だからビラソルよりも大きいものをプリザーブしてるんですね。なんだけど RCFT であってだからそれはだから C をプリザーブするようなトポジカルラインをキャストしろというのであればこれでダイアゴナル RCFT がこれでフラインディラインができるんですよ。だけどトポジカルなビラソルだけプリザーブするっていうトポジカルラインは何っていう質問があって、そうするとビラソルについてはこれは RCFT は一般にはビラソルについてはラッショナルじゃないので、プライマリーが無限に超えるので、ビラソルプライマリーが無限に超えるので、そういうやつに対してどうやってトポジカルラインをクロスパイするかっていうのはオープンクエスチョンでテクノロジーがないので、なるほど、はい、ということでした。 Mic test.
Okay, hello everyone. Welcome back. And I think it's time for us to resume. And the afternoon lecture will be given by Professor Omori, and he will continue his lectures on non-invertible symmetries.
Okay, thanks. So I continue the lecture in the morning. Okay, so I was talking about, so I introduced the algebra object, algebra operator. And so then I'm ready to introduce half space gauging. Okay, so in the morning I said that the gauging corresponds to inserting a mesh of algebra on your manifold. So gauging corresponds to insert some mesh. Well, in this case, just this is enough. Okay. So maybe I comment on that. So this algebra contains some in its definition. So if we expand like this, it's easier to recognize in this picture. Okay, so then something like this, and G1, G2, and G2, G1, well, maybe just say G3, and this should be G1 and G2. Okay, so a way of recognize this as a gauging, well, I said that this is nothing but what Polchinski defined, but I can say in my own words. So this is like, you can recognize the region separated by this mesh. In this case, just this and that. So this mesh is effectively divide this torus into two. Actually, just one single patch. Sorry, this and this is. Sorry, I should draw nicely. Just a single patch, but cut along the mesh. Okay, so you get some single patch, but with I don't try to do correctly, but with the label on its boundary. Okay, and this label, the group element, specifies that how you identify your field on this side and that side. Okay, so you glue the field here and there, twisted by this group element, and here you use different group element, and blah blah. Okay, so that defines one background, so discrete gauge background, and this is sum. So there's a weight. So you are summing up over the possible background, which is a gauging. So that's right. And as Sansu said, these discrete Taylor angles can be recognized as the discrete version of Taylor angle. Good. Now, so this is about doing gauging on the whole space-time, but of course we can easily do the same procedure on subspace of it. So in particular, you do on half space. So let's say we are in a flat space, and I gauge this part. Okay, so I insert some mesh here. Okay, but terminate along this line. Okay. So then here, so I start from some theory T, and I insert mesh on the half of space. So space-time, sorry. So in the end, I get the interface between T and T over G. This is gauged theory. And this is topological by construction. So this A, the algebra, is just a sum of the topological lines or topological operators. So this is, yeah. So A itself is topological. So you can just deform this boundary of mesh topologically, so that immediately tells you that this interface is topological. Okay, and maybe I should say that include the information about the discrete torsion. Okay. Okay, so okay, so I call this interface N. Yes.
Is there a choice of boundary conditions when doing this half space gauging, or there is a preferred choice or a unique choice?
So good. Let me see. So here, I choose this like the G Shure. I think doing something like let me see. I should know the answer, but yeah, I think trying to do like Neumann requires some additional degrees of freedom, something. So in general, the topologicalness is guaranteed is the Dirichlet boundary condition. Of course, you might come up with some non-topological boundary condition, more general, but yeah, I think the most universal topological construction is this. Is only this. Yeah. Okay, so what? Let's think about what happens if we do gauging on an interval. Okay. So here is some mesh, and so this thing is like and bar defines an topological interface from T to gauged version, but then I terminate the mesh here, so that defines. I mean, this part is orientation reversal of this, so it's the n bar, the dual of the interface. Okay. Now it's easy to compute the fusion of these two interfaces. Just crushing the two, and what you get is, so because of the nice property of the algebra, I introduced to you, that like you can do freely deform your mesh. So in the limit, you crush the two boundaries, you just get the algebra itself. So n bar equals to A. And I recall you that A is sum over the line. Okay. Okay, and this is non. Okay, so this G is sum over the elements in the group. In particular, it has an identity, but other elements. Okay. Okay, so this is nothing but the non-invertible. Okay, but this is not yet the operator inside the theory, but this is an interface. So okay, so n is not a symmetry inside T yet. Okay, but anyway, this is a topological interface which is non-invertible. Okay.
Can you repeat the argument why the fusion gives you the algebra?
Sorry,
that equality. How does it follow? N bar equals A. Could you repeat the argument?
Why this equality?
Yeah.
Okay, so n is defined by just inserting a mesh in the half of spacetime, and n bar is defined like terminating that here. Okay, so and then to compute the fusion, I shrink this interval, but there are so you can do whatever you want. So like if you have like something like this, then you can first let me do like there's associativity. So did I wrote something is wrong? Yeah. So first uses associativity here, and then also there, and then I said that there's a way you can erase this bubble to like this. So you can use combination of these moves. There are allowed move. Basically just associativity, recombining this multiplications, and also you can remove this bubble, and you can combine these moves to simplify this mesh on the interval into just a single line. Okay. So that's the argument. Now I have not found any non-invertible symmetry yet, because this is interface. So for this to be a symmetry, I need the non-trivial statement, which is duality. So okay. So if T over G is isomorphic to the original theory, then N is non-invertible symmetry. Sorry, here?
Yeah, to get to the final sum of a single G only. you illustrate eliminating certain lines, I mean, using this rule, but
yeah.
I mean, after doing that, you have 2 horizontal lines, and until you have 1 horizontal lines left, you can repeat that process to eliminate everything. That's what you're saying.
No, yeah, here this mesh should be fine enough, so there should be a line connecting the 2 ends.
But you should have only 1 line left to get the final expression for the algebra, right?
Yes, yes.
So
yes.
you're saying that that can be done?
Yes.
Which
yes.
I think you have checked.
Yes,
Yes.
Thank you,
Thank you.
Yeah. Okay. Oh yeah, so I'm saying this. So this trick is to enables us to recognize this kind of duality as non-invertible symmetry. So most basic example of this kind is 2D Ising, so 1 plus 1D Ising model. And this duality is called the Chromos-1 duality. So the general statement of the Chromos-1 duality is that Ising of temperature T, so here I'm talking about using the notation of the 2D statmic model, but it also holds for this quantum mechanics, quantum Ising model, 1D Ising model with transverse magnetic field. And okay, sorry. The statement of Chromos-1 duality is that Ising model at temperature T and gauge Z2 is isomorphic to Ising model on the dual temperature. And I don't remember the dual, what the dual temperature is. It's a tangent hyperbolic, is log, something like log tangent hyperbolic. I wrote somewhere. Okay, I cannot find it. Okay, but okay. So the point is that if T is low, is small, then its dual temperature is high temperature, and vice versa. Okay, so if I draw, so there's a critical point, and the Chromos-1 duality acts like this, but up to Z2 gauging. Okay, so for at the general temperature, of course, the 2 sides are not equal, and one is ordered phase and the other is disordered phase. So obviously not the same theory, but at the critical point, T equal TC. Then Ising model. So critical Ising model is self-dual. So this thing is that. Sorry, Ising itself, TC. Okay, and this is Z2. So n bar n squared equals to 1 plus theta. I haven't explained that oh yes, sorry. Yeah, so okay, n bar equals to 1 plus theta, just from that general formula, and this eta is Z2 generator, Z2 topological operator. Okay, and I don't prove, but in this case, n bar is actually self-dual n. Okay, so this is n squared, and this is nothing but the Ising fusion rule. Ising CFT fusion rule. Okay, so so this, yeah, in this particular case of Ising CFT, this non the Faraday line contains this non-invertible symmetry, non-invertible line, and that can be beautifully reinterpreted as symmetry associated to the Cronmas one duality. And so unfortunately, I don't have enough time to explain this Cronmas one duality enough. But what happens, it's educational to think about the action of this non-invertible symmetry on a local operator. So say pick the spin, and it is well known that this under the Cronmas one duality, its spin operator becomes a disorder operator. And what it means is that so this n is topological. So consider this configuration and push n towards this way. So you get something like this. Maybe this. And so and this is sigma and okay. Then fuse this part, you get n, but here you have 1 plus eta and some operator. So it turns out for usual symmetry, I mean for conventional symmetry, what you get, I mean some UG and some O, and what you get is that do the same procedure, you come to the same thing here, okay, and fuse this part. But for the old conventional symmetry, the UG times UG inverse is just 1, and there's no other component. Okay, so here you use just a trivial operator. Okay, and okay, so this procedure gives you just G action on the operator. Okay, if you move this topological operator through the local operator, we just let this symmetry acts on the operator. However, for the non-invertible symmetry, you might get the line topological, I mean surface, some extended operator stretching between this topological operator and your local operator. In this case, line. That's the most general thing to happen. And in the case of Ising model, what you get here is the disorder operator. Which is actually at the end of eta. Okay, and yeah, sorry. Yeah. So this one component, there's 0 at the end, and for the eta component, there is a disorder operator. That's a special case of Ising model. Yeah. So this disorder operator on lattice is just, so if you recall, if you have this Z2 line, then you modify this Boltzmann weight. But then this disorder operator means that we just abruptly terminate this Z2 line. That's a disorder operator. Okay. And this disorder operator is not topological. This eta is topological, but this is not of course not topological. Defect operator. Okay. So in the first lecture, if you recall, I said that these topological operators gives you a generalization of what Takahashi identity. So what identity do we get in this case? So start from like sigma to 2 sigmas inserted and correlation function and put n here. I'm talking about the critical Ising model. And so there are 2 ways of evaluating this configuration. One is contract this n towards the infinity. Okay, so let's say I'm working on T2. Sorry, I'm working on S2. Then I can contract this n line at the infinity. So then I get, so this is a contract n at infinity. Then, so contracting a topological line gives you a number, and actually you get square root of 2. Okay, so that's one way. Okay, so this is square root of 2 is just a loop. A loop of loop expectation value of n, which is square root of 2, and that can be understood that n squared equals 1 plus eta, and so this is called the quantum dimension of n, and these have dimension 1. And so the sum gives you dimension 2. And this quantum dimension just of the squared operator should be just the squared of quantum dimension. So this should be QDim. So the quantum dimension of n squared is 2. So quantum dimension 1 loop expectation value of n is square root of 2. So that's here. And I can also shrink this n towards the origin some point, and what you get is this. So it's a two-point function of disorder operator. Okay, so in general, the equation provided by the non-invertible symmetry involves both the local, the operator, genuine operator means that not the end of other topological line, and the defect operator, which is at the end of other topological operator. Okay, and this kind of thing does not happen in the conventional case. Okay, so this is the one node generalized Takahashi identity. Okay. And okay, so there's also an implication on the potential phase in from the non-invertible symmetry. So that's okay. So we have Kramers one duality, and that gives us a topological line n. Okay. Okay. So okay, we have this line on the lattice even, and then without analyzing anything other than the existence of n, that we know that in the IR or continuous limit also admits this topological line, because this is topological, so it doesn't care about the scale you are working on. Okay, so that leaves two possibilities. Well, first, this this leaves two possibilities. One is critical. So IR possibility. And second is multiple vacuum. But there cannot be single. I mean, okay. So to exclude this possibility, if Ising flowed to this single vacuum, then this should admit this topological line n. But that's obviously wrong, because so having n means that single vacuum is isomorphic to single vacuum. I mean, trivial theory, modulo Z2. But if you gauge the Z2 acting trivially on trivial theory, you get two vacua. So these have two vacua. So this equality doesn't hold. So this single vacuum is not a candidate phase in this theory. Of course, this 2D Ising model, critical Ising model, is solvable, and we know that this is the answer. But yeah, anyway, that's the way to use asymmetry. Okay, so let me give you a cooked up example of two. So this is kind of stupid example, but I consider Ising model and stacked with Ising model with its dual temperature. Okay, so let's say this is in ordered phase, and this is disordered phase. Okay, and then by construction, so if I gauge Z2 times Z2, for each copies of Ising. Stacking means that I just put the two lattices on top of each other and do not talk. They do not talk each other. But this is just a toy model. But if you gauge Z2 times Z2, then of course you get by invoking Kramers-Bonnier duality twice. You get this. Then of course you can freely swap the two sides. Okay. So this is self-dual under. So this is self-dual under gauging Z2 squared. Okay, so there's a corresponding non-invertible symmetry whose square equals to, again for the same reason, the n bar equals to n. And so is this, maybe I say tensor, where eta 1 acts on the first copy of Ising and eta 2 acts on the second copy of Ising. Now, of course, we know that this system, so let's say that T is not critical, then we know that this is gapped. So not critical, but have a multiple vacua. It has multiple vacua because one of them is in the ordered phase. Okay, so it's interesting to study, explicitly study how this symmetry acts on this system. So take T goes to 0. Yes. And here I'd like to working on the quantumizing, so and switch to the 1 plus 1D quantumizing with transverse magnetic field. Okay, so then rather than the static model, so that I can talk about the quantum states. Okay, so then the vacua are, so from first copy of Ising, we have up. This means every spin is up. It's 1 plus 1, so 1D Ising chain, quantum Ising chain, and so from first copy, it's down, down, down. Okay? So in the ordered phase, the second copy it's in the disordered phase, it's infinite temperature. So I got the cross, which is up plus down tensor. I mean, up plus down, up plus down. For each spin. Okay, so each spin is in this superposition. Now, so in the stacked model, therefore we have two vacua. Okay, And so now there's action. There should be action on this vacua, on action of n on this vacua, and what it is. Okay. So n somehow, very roughly speaking, exchange the two factors, right? Here, I do gauge, but then this t becomes tv and tv becomes t, so I have to swap at the end of the day to make these two isomorphic. So n kind of swap this factor and that factor. But of course, you cannot do it literally. So what it does is, okay, so here I just give you the answer without derivation, and I will do just a small consistency check. But what it does is that it sends this state to here, but there's only one vacuum, so up becomes cross. Then cross is, this is Z2 invariant, and n doesn't break this Z2 invariance. So this cross is sent it by the state here, which is Z2 invariant. The only candidate is up plus down. Tensor cross. So this is the action. And recall that this is a plus, plus, plus. Sorry, up, 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 plus, down, down, down. And cross is just the disorder. Vacuum. Okay, and you can check that n squared. So n squared of on this vacuum. By the way, the same. This is the same for acting on the other vacuum. And if you do n squared, you get I believe I hope I'm yes, 2 of up, down, tensor cross, and on the other hand, this n squared I wrote there, that 1 plus eta 1, 1 plus eta 2. And this guy, so eta 1, of course, swaps these two. And the eta 2 acts on this state, but it makes it invariant. So it gives you 2, and here, so it's consistent action. Now, why I wrote this explicit expression in this stupid example is that I'd like to show you that n, the non-invertible symmetry, does create an entanglement. Okay, so these all of these vacua are zero entanglement entropy with respect to any subregion. It's just a tensor product state. Okay. Now, the n gives you all up plus all minus or all down, which is nothing but a Bell state, and for any bipartite separation. So this, so n injects, not always, but some, depending on the state, but and these non-invertible symmetry can inject entanglement. Okay, so that's. I mean, I don't know what it is good for, but I'd like to emphasize this part of this aspect of the non-invertibility. Now, oh yeah, yes. So, so whether or how much of entanglement is injected is also depends on your state. For example, this n makes this critical Ising model, the vacuum of critical Ising model invariant. So in that case, n does not induce any entanglement. But in general, yes, there's a there's a phase where this n in non-invertible symmetry is spontaneously broken, and this is one example. And in such case, yeah, in general, this kind of sum appears, which means that the entanglement is induced by the action. Yes. So yeah. This of course stems from the fact that this fusion involves the sum. That's a superposition. Okay. Okay. So far I've been talking about 1 plus 1D, so I also introduce 3 plus 1D example so that the title is fulfilled. And one good example is the free Maxwell. So as I said, the free Maxwell has just a pure U1 gauge theory. Has a U1 one-form symmetry, and let me talk about the magnetic one-form symmetry. And so the action of the symmetry on the theory is such that if you bring the fifth line and let this symmetry operator, this is magnetic one-form symmetry operator here, and acts on the fifth line, which is the word line of probe monopole. Okay, this is monopole. Then it just measures the magnetic flux coming from the monopole, so you get this phase. Now you can pick some Zn subgroup of U1 and gauge. And what happens is, so if you gauge, so the gauging, the original symmetry is continuous, but I pick the discrete subgroup, so I treat it as a discrete symmetry, and gauging is done by inserting a mesh of this thing. So this thing is codimension 2 in 3 plus 1D. But anyway, you can do the same thing, and to be precise, this consistency condition about associativity is replaced by something else. But in this case, there is nothing vary sum. So you can just have form the algebra operator, which is now two-dimensional, and you sum over the Zn elements. And this is your algebra, and insert the mesh of this two-dimensional thing in 4 dimensions. Okay, so that can be done. And what happens is that because you're gauging the Zn subgroup of U1 magnetic one-form symmetry, so Tn, small n, maybe just m, Tm is projected out when if m is non-zero mod this n. Okay, that's because basically you are inserting, like if you put Tm here, but then you insert A is just a sum over this topological operators, and that becomes sum over the phase, but you get 0 if this combination is not multiple of 2 pi. Okay, so after gauging, you get only T Kn exist. So if we write F, the field strength, of the original theory, after gauging, okay, so this is quantized so that any two surface, it's in maybe 2 pi here. It's in Z, but after gauging, because these fifth lines are, some of the fifth lines are gone, so the quantization of, possible magnetic flux is only the multiple of n. Okay, so after gauging this F, this F is not properly quantized in the sense that it only takes values in the multiple of n. So, what I'm doing here is not terribly correct, but as a heuristics should work. And to get the correctly quantized field strength, we define F tilde, which is F divided by n. Okay, so original action, if the original action is just a free Maxwell with this, okay, then well, gauging does not directly affect this action in terms of the same variable, because this one-form symmetry does not act on the local operator, so the only effect is through the change of quantization, and but just substituting this, we get this thing. And after gauging, the F tilde is the correct field strength. Okay, so this tells you that E. So nu E tilde is E over N, or tau tilde is tau n squared tau, where tau is the usual complex coupling, which I don't remember, the 4 pi I g squared plus theta over 2 pi theta over. Here I just write E. Okay. Okay. So free Maxwell. If we start from free Maxwell with tau and gauge this Zn magnetic one-hot symmetry, Zn subgroup of magnetic symmetry, then this is free Maxwell with tau n squared tau. So this is the scaling of tau. Okay, so this is just the computation of what happens when we gauge the subgroup of magnetic symmetry. But then we also use the fact that there is an electromagnetic duality. Okay, so there's an electromagnetic duality. And that means tau free Maxwell with tau is isomorphic to free Maxwell with minus 1 over tau. By rewriting your gauge field with a dual gauge field and exchanging electric and magnetic charges. Okay, so combine this, that free Maxwell tau over the Zn magnetic one form. Okay, so it is dual to free Maxwell. So first we get the n squared tau, but then I invoke the duality, so minus 1 over n squared tau. Okay, so if tau, set tau equals to ni. So the setting this coupling to a special value. Okay. Then okay. Then this free Maxwell and with tau equals to ni, particular value, gauged by the n magnetic one-form symmetry, is self-dual. It is dual to itself, the original theory. Okay, so free Maxwell will. So photon, yeah. This involves the electromagnetic duality. So well, yeah, photon goes to photon. Yes, that I guess is yeah. It's more like this is more like about the lines. So Wilson line becomes the fifth line, but the yeah. Yeah. Yes. Yeah. But here I also use the duality, which yeah. Yes. So okay. Okay, so this free Maxwell theory, the tuned coupling has self-duality. This kind of self-duality. Okay, and oh, by the way, I should have said so this is found by the Cordova. No, sorry. Choi, Cordova, and Shin, Lam, Shao. I hope I ordered correctly. Okay, okay, and that's come 2021. Okay, so this means that there is a duality topological surface. This is codimension 1 surface. Good. So, okay. So as a picture, and sorry, tau equals to ni. Did I do correctly? So no. I here. So I think this is correct. Okay. I over. So this is codimension 1. Sorry for the camera. I'm going back and forth. So sorry. And so first, let's recall that first, well, for general tau, we have a topological interface by constructed as just as a mesh. So now this is a codimension 2. So my writing is not very good, but I can draw 4 dimensions. Okay. So what is n this n? And for the tuned tau equals I over n, this becomes the interface between the free Maxwell and itself. So it becomes a symmetry inside a single theory. And what is n bar? And in this case, okay, so I draw the same picture here, but there's a difference from the in Ising model 1 plus 1 decays. So n is codimension 1, simply because it separates at the general value of tau, it separates one theory to the other. Okay, so it has to be a domain wall between the theories. Okay, so it is codimension 1. But this mesh is of codimension 2 is dimension 2. Okay, so the direct generalization of the Ising model case like this does not make sense, because this is codimension 1, this is codimension 2, and there cannot be equality. So what happens is that if you squash this interval, then so I suddenly draw the other direction, and you still have a mesh, but okay, so you from the start you have this mesh filling 4D space. Yeah, there's other 3 dimensions. I mean this is x direction and y z t here. Okay, so there's a mesh here, and squashing this interval along the x direction, you still have a mesh, but stretching only along the yzt. Okay, mesh of A. So this is this thing. This is like a codimension 1 mesh of A, which is codimension 2. Okay, so this is called condensation, or by the condensed matter terminology, or called one gauging by this. The latter name is introduced by Rumperakis, C. Funashiri Shao. And so one gauging means the 0 gauging is the usual gauging I introduced, and one gauging is gauging only along the codimension 1 surface. Okay. Yeah. And the condensation generally refers to just thinking about the mesh and making the mesh finer and finer. That's the intuition of the name condensation. Okay. So the point is that this A satisfies a good axioms, so that this detail of mesh does not matter. So it should be fine enough, and but you pick any mesh fine enough, and then should give you the same answer. Good. So this is condensation. Sorry. Fine enough. So well, I cannot give you the definition of when it's fine enough, but like, okay, I can give you the example of when it is not fine enough for example, if you have a torus and you just put A wrapping the one of the cycles, and this is not fine enough. This is not fine enough. So roughly speaking, this A should going around all the possible cycles, and yeah. So that's the yeah. So mathematically speaking, so one can show that if we keep adding the additional segment of A randomly, then at some point the correlation function, the value of correlation function stabilized against the adding additional segment. Okay. So more explicitly, if we say that this world volume of defect or the operator is M3, then it's like summing of a Zn cycle and some number here, and for any possible Zn cycle, you insert U of 1. This is Zn cycle S, and 2 pi over n on this cycle. Okay. Inside M3. M3 is a three-dimensional thing, submanifold in the spacetime. So that's the world volume. And this condensation is explicitly just the sum over possible insertion of your Zn one-hot symmetry generator. So this is 2 cycle. S is 2 cycle. Okay, so yeah, so this is okay. So this is not explicitly the form of 1 plus something, but in here, particularly in particular, there is a trivial cycle that's like the plays a role of 1, and then sum over the other insertions of the lower dimensional thing. So that's the general structure happening in higher dimensions. Sorry.
N bar is equal to condensation is quantum exact.
Condensation is what? Sorry.
I mean, if we include, we can include quantum corrections to that relation, then there could be some correction from the quantum effect. But what about quantum effect?
So here I'm talking about the free theory. So in that sense, it's just free, and that exact electromagnetic duality is holds only for this free theory. And if you add, for example, some matters, then it breaks down. So in that sense, this is kind of special for free theory, and or some particular theories, I should say. There are interacting examples, but very special. This kind of thing happens on a special point, and yes.
It seems to be trivial statement.
Well, free theory being trivial is too strong statement. There are many interesting things in free theory, I'd say, but on the other hand, I admit this is just a toy model, and partly convincing, but not thoroughly convince ourselves that this non-invertible symmetry exists in the more realistic world. So I give you other examples. By the way, how much time do I have? 5 minutes. Okay. So I'm going to give an example more relevant to ourselves tomorrow, and I finish saying something else, which is other example. Which is, for example, the 4D. Oh, first thing is I should say that 4D. There's 4D version of Ising, and this is by Koide, Nagoya, and Yamaguchi-san. And so there's a 4D version of Ising model, and there's a generalization of Kramer-Svania duality. So this is again the same as very similar to that. And again 4D n equals to 4 super MLs. And here I say SUN at tau equals to I. Okay. So super MLs, although it is interacting, but it's known, or it is widely believed that it has S duality, so electromagnetic duality. However, for SUN gauge group, the S duality sends it to PSUN. Is SUN modulo Zn, which means that the spectrum of the line operators of here and there does not exactly match. Okay, but this PSUN gauge theory can be obtained by gauging magnetic one-form symmetry of SUN. So here, in general, the n equals super MLs, I mean n equals 4, and SUN, and tau, and if you gauge the Zn, n is the same n, magnetic symmetry, you get super MLs of PSUN with the same tau, but then you invoke S duality, then super MLs of SUN minus 1 over tau. Okay? Then you tune tau to be I, very strongly coupled point. Okay. Then this is super MLs of tau equals I is self-dual under gauging Zn magnetic one-form symmetry, and therefore have the same type of symmetry. Okay, and yeah, and you can also thinking about other gauge group or involving other choice of global form of gauge group, the choice of Taylor angle, blah blah, and thinking about more general cluster theory, and all kind of things are done mainly by Justin Cady and his collaborators. So that's, yeah. So I finished today. Yeah. Yes.
Can you say what is four-dimensional Ising model? Is it a CFT or just a lattice model?
This is a lattice model, and for Zn, for Z2, so they worked on Z2 case, and Z2 case, the critical point is believed to be gapped, so it's a first order phase transition. Yeah. In large N, it's believed that it's critical, and it's interesting to fit. Probably to the free Maxwell, but I don't have the evidence for the like Z5 version of Ising. I think it's believed to be critical. And yeah. Okay, any other question?
You showed the construction by half-space gauging. Then my question is, can we understand this defect in terms of one dimension higher viewpoint, like as far in the line?
Yes. So yeah, in this lecture, I do not plan to talk about those symmetry TFT business, but indeed, yes. One can consider some 4D theory with one form symmetry. One form symmetry, some Zn, one form symmetry. Then you can naturally couple it to a 5D BF theory with two form B, D, B prime, two form, and BF theory. We are like this B2 acts as a background of this Z and one form symmetry. And yeah, so then there's a viewpoint of relating this duality and the electromagnetic symmetry in 5D. So there's a Z2 electromagnetic symmetry. This is invertible symmetry in 5D acting on the BF theory, and there's a relationship of this invertible symmetry and okay, so and this non-invertible symmetry in 4D. Yes.
Thank you very much.
There's a story. Yes.
Okay, so free Max will also have a U1 electric one-form symmetries. Do you get some new information from gauging it?
So you want what?
One-form electric.
Electric. Oh yeah. So I explained in one way that's the electric, and the going back is done by electric gauging electric one-form symmetry. So you just.
So the duality just exchanges the electric and magnetic.
Yeah. Yes.
Okay.
Yes. And yes.
So is there any relation between anomaly-free condition for half-space gauging and usual anomaly-free condition for entire space?
So for half-space gauging, you need the symmetry to be anomaly-free. It should be gaugeable.
So if a symmetry is anomaly-free for usual sense, then we can always do a half-space gauging.
Yeah. To define this the higher codimensional mesh. So the constraint to do higher gauging is weaker than constraint for the zero gauging. So there is also the notion of higher anomaly that when you can do this kind of higher codimension gauging, and yes, so that story is also in this Rumpedakis, Saifunashi, Shao paper.
Okay. Yeah. Thank you.
So if we start path integral approach to the pre-Maxwell with magnetic one-form symmetry, then action itself has this magnetic one-form symmetry. Then what is the source of this non-invertibility from the path integral point of view?
Okay, so there is a explicit construction in the paper, and explicit construction in the paper by Choi et al. And of this defect, and in that formulation, well, we are going to see a very similar thing tomorrow, but there's a topological degrees of freedom living on this defect. So it's not just a way of understanding this non-invertibility is that it's not just the usual symmetry is just enforcing some symmetry action on fields as a transition function, but here this topological defect has topological degrees of freedom, its own topological degrees of freedom on its world volume, and that produces a non-invertibility.
That is non-dynamical?
It's dynamical only on this defect, the world volume of operator. Yes, it's sort of just something. Yeah, we are going to see another example. Yes, tomorrow.
I have a kind of naive question. You said n equal 4 super Yang-Mills says non-invertible symmetry at tau equals minus I or something. Does that non-invertible symmetry has correspondence to the bulk ADS5 theory?
Oh, so how you can see this kind of thing in the ADS5?
Yes.
So Francesco might know, but I. Yeah, in a sense, yes. Yeah, so yeah. One way is, of course, is that this kind of BF theory is inside this supergravity, 5D supergravity, so it's related to this EM duality on the. But do you know the explicit brane that corresponds to?
It's a 7 brane.
It's a 7 brane. Okay, good. So.
Okay. Are there more questions? Okay. Otherwise, let's thank the speaker. We conclude today's sessions.
I cooked up yesterday, so I don't know.
Could you go into that color entanglement injection?
Yes. I haven't. That aspect haven't never been emphasized other than myself. That's kind of yeah.
So it was about, I mean, when you put the n squared, right?
Yes.
1 plus something, so it's change a little bit. You increase entanglement.
Yeah. So there's a explicit way of So there's a explicit implementation of this action on the spin chain, and that's like